The night is deep and silent. Under a moonless sky, the stars shine freely, thousands of ancient lights glittering in the darkness. In this stillness, you can imagine lying back against cool sand or soft grass, gazing upward. Without the glare of modern cities, the heavens glow as a river of stars, a band of pale light stretching from horizon to horizon. It is the Milky Way, our galaxy seen from within, a ghostly white path that our ancestors once saw clearly every night. In times long past, before electric lights and busy minds, people looked up at this same sky in wonder. They watched the patterns of stars slowly wheel above and felt connected to something vast and eternal. Every point of light held a mystery. To ancient eyes, the night was alive with stories written in the stars. They traced figures among them: a great hunter chasing his prey, a mighty bear rising on hind legs, a dragon winding across the cosmos. Different cultures imagined different forms in the sky, a cosmic canvas for their myths and legends. The Milky Way itself was a source of legend. Some called it a celestial river, flowing with souls or divine light. Others saw it as milk spilled from the breast of a goddess, strewn across the night. On a clear evening far from human settlement, as you gaze up, you might see a shooting star streak across the sky, a brief, silent flash. Such a sight might make you gasp now. To ancient observers, it could have been a sign from the heavens. The stars were constant companions, yet sometimes the night brought surprises. A new bright star that hadn't been there before, the slow wanderings of planets, the glowing tail of a comet. Each event fed the imagination with wonder and a touch of fear. Yet mostly, night after night, the stars returned in their familiar places, reassuring in their permanence. As the earth rotates, the constellations rise in the east and set in the west, as if the whole sky is turning around us. It's an illusion born of our own planet's motion, but to the first stargazers, it was the sky itself that revolved. They built monuments to mark the turning seasons by the stars, stone circles and temples aligned to the sunrise or to the North Star, Polaris, that steadfast point around which the heavens appear to pivot. For centuries, Polaris has guided travellers in the northern world, hanging almost directly above Earth's north pole. On any clear night, it remains fixed in the same spot, while all the other stars slowly circle around it. To those journeying across featureless deserts or uncharted seas, that little star was a beacon, an anchor in the cosmic ocean. Beneath ancient starlight, humans found their direction, both physical and spiritual. Over time, we learned that those stars are not just lights on a dome, but distant suns shining across unimaginable space. Yet even before science revealed their true nature, people sensed that the stars were old, far older than any human memory. There is a quiet truth in that intuition. The starlight we see tonight began its journey ages ago. Light moves incredibly fast, around the globe 7 times in a second. Yet the stars are so distant that their light can spend centuries, even millennia, crossing the void before it falls gently upon our eyes. Consider the star we know as Polaris, the North Star. It lies about 400 light-years from Earth. That means the light guiding an explorer tonight set out around the time when Galileo first pointed a telescope to the heavens. Farther still, the star Deneb, twinkling in the summer sky as part of the Northern Cross. is around 2,500 light years away. Its radiance began traveling toward us before the pyramids were built, before writing was invented. A silent journey through eons of time and emptiness, arriving only now to meet your gaze. When you look at Deneb on a dark night, you are seeing a beacon from a time long lost to human history. The past flows down to earth with every shimmering ray. Think of the faint glow of the Andromeda galaxy, the most distant thing visible to the naked eye. To us, it appears as a delicate smudge of light on a clear night, just on the edge of vision. That hazy glow is not a single star, but an island universe of 1 trillion stars, each one too far to distinguish individually. The light from Andromeda has travelled for 2.5 million years to reach Earth. On the night it began its journey, our early human ancestors were chipping stone tools, and the world was a very different place. Yet here and now, that ancient light becomes part of our night sky, bridging a gulf of time. Under ancient starlight, we are literally witnessing history written in the sky's faint glimmers. High above, the stars seem eternal, but they too are living entities of a sort, born and dying on timescales beyond comprehension. Ancient storytellers could not know of stellar life cycles or galaxies, but they felt the power and permanence of the night sky. It gave them a sense of order and continuity. The same stars returned each season, heralding planting times or winter's onset. Over generations, star patterns shifted ever so slightly. A bright star might move a bit from where it was seen by a great-grandparent, almost imperceptibly. Only now do we understand why. Everything in the cosmos is in motion. But to those who lay under ancient skies, the slow drift of the heavens was subtle beyond notice. To them, the heavens were the one realm that seemed unchanging, even as empires rose and fell beneath. There is comfort in that timeless perspective. Imagine an elder thousands of years ago, pointing to the night sky and telling stories to the young gathered around a fire. The faces of the listeners glow softly in the firelight, but their eyes are drawn upward to the sparkling dome above. The storyteller might say, "See that star there, low on the horizon? My father saw it when he was a child, and his father before him. It will shine long after we are gone." In that moment, under ancient starlight, each generation finds continuity with the next. The cosmos above was a shared inheritance, a constant from past to future. Even today, when we step away from our illuminated cities and find a dark field or mountaintop, we can recapture some of that ancient awe. The Milky Way arches overhead like a bridge made of misty light. You may feel the weight of the ages looking at it, knowing that countless others across time have stood in that same darkness, marveling at the same glowing band. We now know this band is the disk of our own galaxy, seen from inside, a vast spiral of stars in which our sun is just one tiny spark. But that scientific understanding doesn't diminish the wonder. If anything, it deepens it. The more we learn, the more profound the night sky becomes. So we lie there, heart quiet and mind calm, bathed in the gentle glow of ancient starlight. These stars are our oldest storytellers. Their light speaks of distances beyond imagining, and times so long past, our minds can barely grasp them. We realize that, in a way, we are time travelers, observing a universe that is not as it is now, but as it once was. Every star is a reminder that the universe is vast in both space and time. Above all, the night sky reminds us of our connection to the cosmos. The atoms in our bodies were forged in stars that lived and died billions of years ago. When you gaze at the stars, you are seeing pieces of what ultimately became you. It's a humbling and yet comforting thought. We are part of this grand story. As the night deepens, a gentle breeze might stir, but the stars remain steady. They invite us to ponder big questions with a quiet mind. How far does this universe stretch? What lies beyond the stars we can see? It is a mystery that has always beckoned humanity. Under the canopy of those ancient lights, we begin our journey through the cosmos, guided by curiosity and imagination. The darkness above is not empty. It is filled with suns and worlds beyond counting. And though those pinpoints of light seem fixed and still, patient observation reveals that they have their own rhythms. A few among them wander against the backdrop of their brethren, moving in slow, stately paths. Our ancestors noted these special travellers, bright lights that, unlike the rest, did not stay in their constellations. Over weeks and months, they drifted, tracing loops and arcs in the sky, as if dancing to hidden music. It was the first hint that amidst the apparent stillness, there is a celestial ballet underway. They are the wanderers, the planets. To early sky watchers, they must have been mysterious indeed, bright points of light that moved against the backdrop of the starry firmament. In fact, the very word planet comes from an ancient Greek term meaning wanderer. These 5 visible wanderers, Mercury, Venus, Mars, Jupiter, and Saturn, stood out precisely because they refused to stay put in the sky. Night after night, they inched forward, sometimes even appearing to loop backward for a time before continuing on their way. It was as if they danced to their own subtle rhythm, while the other stars formed a fixed chorus. For thousands of years, their true nature remained unknown. But patient observation and the advent of the telescope gradually revealed what they really are: worlds. We learned that Earth is one among these planets, and that all are travelling in orbits around the Sun. The night sky's grand design began to make sense. These wandering lights were not errant stars at all, but our cosmic neighbours circling the same star that gives us day. We had discovered the celestial ballet, a dance of planets and moons bound by gravity, moving in tune with the sun's gravitational music, like dancers linked by invisible threads. Imagine rising above the solar system, watching from high above as the sun's family moves. You would see the planets tracing paths around the sun, each following an ellipse, a slightly stretched circle. Mercury scurries along its tight orbit nearest the sun, completing a circuit in just 88 days. Farther out, Earth takes a year for its journey, and beyond, stately Saturn needs nearly 30 Earth years to go around once. At the very edge, Neptune, cold and distant, takes a leisurely 165 years to make a single loop. Each planet keeps to its track, a cosmic dance floor laid out in the vast, dark space. The closer a planet orbits to the sun, the faster it travels, as if eager to complete the next lap. The farther away, the more sedate its pace. Yet all move in harmony, each held in the sun's gravitational embrace. From our vantage on Earth, we experience this dance in subtle ways. The most immediate is the cycle of day and night, our planet spinning like a dancer, twirling once around each day. At dawn, we turn our faces to our star, basking in its warmth and light. At dusk, we spin away again, and the stars emerge as our part of Earth faces the depths of space. This daily pirouette connects us to the cosmos. It is why the sun rises and sets, why the constellations march across the sky each night. And as Earth spins, it also moves along its orbital path around the sun, carrying us through the seasons. Our world tilts as it circles, leaning toward the sun and then away, giving us the changing length of days and the ebb and flow of warmth each year. Even if we do not feel it, we are always in motion, spinning on our axis, sweeping around the sun, part of a grand cosmic routine. Sometimes, the choreography of this celestial ballet results in breathtaking alignments. Think of an eclipse, a moment when three dancers, the sun, the moon, and Earth, briefly line up perfectly. During a solar eclipse, the moon glides directly between Earth and sun, and for a few minutes, day turns to eerie twilight as the moon's shadow races across Earth's surface. The sun's brilliant disk is briefly covered, leaving only a delicate crown of light, the solar corona, visible in the sky. In those moments, stars peek out in the daytime, and animals fall silent, confused by the sudden night. It is a stunning display of cosmic precision. The moon is about 400 times smaller in diameter than the sun, yet it's about 400 times closer to Earth than the sun is, making them appear nearly the same size in our sky. By a remarkable coincidence, when geometry aligns just right, the moon can hide the much larger sun completely, treating fortunate observers to one of nature's most beautiful spectacles. Lunar eclipses are the reverse. Earth interposes itself between sun and moon. As Earth's shadow falls across the moon, the lunar surface darkens and often glows coppery red under the filtered sunlight bending through Earth's atmosphere. Our planet's shadow gently sweeps over the moon like a curtain. To someone standing on the moon during such an event, the sun would vanish behind a dark Earth, rimmed with a brilliant red ring of all the world's sunrises and sunsets. These celestial events remind us that the cosmic dance is not just an abstract motion. It has real, observable effects that humans have marveled at for millennia. Ancient peoples in China and Babylon learned to predict eclipses, understanding the rhythm enough to anticipate when the dancers would align just so. The ballet extends far beyond Earth and its moon. Each planet is like a dancer with its own tempo, and many have their own partners swirling around them. Jupiter, the giant of our solar system, carries a retinue of moons that twirl around it as it circles the sun, a dance within a dance. In 1610, when Galileo first pointed his telescope at Jupiter, he saw 4 small points of light near the planet, shifting positions each night. They turned out to be Jupiter's largest moons, orbiting that world. This was a revelation. Not everything circled the Earth, as was long believed. Here was a miniature solar system in its own right, proof that the heavenly dance had multiple layers. Once we recognized that Earth itself is a participant in the celestial ballet, our perspective changed. We realized that our planet is not the stationary center of creation, but one moving part in a larger choreography. The sun is the true centerpiece of this dance, shining with the light that illuminates all the planets. Its gravity is the music that keeps time, guiding the planets in their orbits. Even distant Pluto, tiny and slow, follows along, taking over 2 centuries to complete one round. The choreography is complex but elegant. Each planet follows its path, sometimes drawing nearer to a neighbor, sometimes farther, but always bound to the sun's pull. Occasionally, Two or more planets will appear close together in our sky, a conjunction, passing like dancers briefly side by side before parting again. Such meetings have inspired awe since ancient times, when, say, Venus and Jupiter, the two brightest wanderers, would draw near each other at dusk and captivate observers with their combined glow. Beyond the orbits of planets, countless smaller objects join the dance as well. There are asteroids in broad belts and comets in elongated orbits that loop far out and back again. They too orbit our sun, though often with more eccentric steps, like dancers that break from the main formation only to return later. But even these seemingly erratic participants obey the same gravitational music. Remarkably, although this ballet has been ongoing for billions of years, it has a kind of stability. The planets trace and retrace their steps reliably. Over immense spans of time, the dance does evolve. The pull of the planets on each other causes slight changes in orbits, a gradual shifting of patterns. But on human timescales, the music seems eternal and unchanging. Think of how gracefully balanced it all is. If the sun's gravity was somehow switched off, the planets would fly away into space, each on a straight line path, no longer tethered. If the planets were moving much faster, they could escape the sun's embrace. If much slower, they would spiral inward. But as things are, each world moves at just the right speed for its distance, a cosmic balancing act that keeps the entire system in motion and in order. Floating in space alongside our world, you would see Earth and our moon together, performing their own duet as they travel around the sun. One side of Earth is always facing the sun, in daylight, while the other side is night under the stars. And the boundary between them, the terminator, slowly sweeps across the globe as Earth rotates. Meanwhile, the moon circles us every month, sometimes between us and the sun, other times on the far side. It tugs gently on our oceans as it passes, lifting tides. All these motions, the spinning of Earth, the orbit of the moon, the journey around the sun, combine into a beautifully orchestrated dance that gives us the rhythms of time we know, day and night, the phases of the moon, the passage of months and years. Under the grand canopy of stars, the celestial ballet continues ceaselessly. Each planet, each moon, each wandering body glides along an ancient route. We are a part of this cosmic dance, whether we realize it or not, riding an orbit around our star on a spinning sphere, accompanied by our moon, in the stillness of a clear night. If you become aware of it, you can almost feel the majesty of that motion. Our ancestors once watched planets trace strange paths in the sky and wondered what they were. Now we know. They are fellow travelers, partners in orbit. Ahead of us, at the center of this ballet, our sun shines brightly, holding its family close. And around that brilliant star swirl the planets, the children of the sun, each with its own character and story, each a world waiting to be explored. A star was born, and around it a family gathered. Our sun, a golden star in the galactic sea, blazed into life about 4.6 billion years ago. In its infancy, it was surrounded by a swirling disk of gas and dust. Over time, that material clumped together, forming the planets, truly the children of the sun, born of the same cosmic cloud as their parent. Now these planets circle around the sun, each following the path set for it since the solar system's dawn. Closest to the sun is tiny Mercury, a scorched and battered little world. Mercury is not much larger than Earth's moon, and it wears a similar look. Its surface is pocked with craters from countless ancient impacts. So near the sun, Mercury is seared by intense sunlight. Daytime temperatures on its rocky surface climb high enough to melt lead, while the night side, facing away from the sun's glare, plunges into deep cold. Mercury has virtually no atmosphere to soften the sun's fury or hold any heat during the long night. The sun looms more than 3 times larger in Mercury's sky than it does in ours, and the sunlight is several times stronger. If you could stand on Mercury at noon, in a magical suit protecting you from the deadly heat, the sun would dominate the sky, brilliant and blinding. Yet Mercury spins so slowly that one Mercury day, from one sunrise to the next, lasts nearly 2 Mercury years. The result is long, scorching days and equally long, frigid nights. In Mercury's perpetual silence, the sun's light beats down relentlessly, and then darkness falls for weeks at a time. It's a world of extremes, a burnt cinder dancing close to the sun's flame. Moving outward from Mercury, we come to a planet of clouds. Venus, named for the goddess of love and beauty. To the eye, Venus is the most radiant planet in our skies, often visible as a brilliant beacon at dawn or dusk. The morning star, or evening star, outshining every other pinpoint of light. But beneath that lovely, pearly white glow lies a harsh reality. Venus is a world swathed in thick clouds of carbon dioxide and sulfuric acid. Its atmosphere is a heavy blanket, nearly 100 times thicker than Earth's, trapping the sun's heat in a runaway greenhouse effect. The result is a planetary oven. Venus's surface is even hotter than Mercury's, despite being farther from the sun. Temperatures soar to about 900 degrees 80 degrees, hot enough to melt lead. The air pressure at the surface is crushing, like being 900 meters under the ocean on Earth. No human could survive there. Even our hardy robotic probes last only an hour or two in those hellish conditions. The landscape of Venus, glimpsed by radar and a few briefly operating landers, is a dry, rocky plain with volcanic features and strange fractured highlands. If you stood on Venus, you'd see a dim orange haze, no direct sunlight, as the sun is completely hidden behind eternal clouds. Strangely, Venus rotates backwards compared to most other planets. On Venus, the sun would appear to rise in the west and set in the east, though you'd never see it through the clouds. Its rotation is extremely slow as well. A single day on Venus lasts longer than its year. Venus, so similar to Earth in size and composition, took a very different path, becoming a toxic hothouse, a cautionary tale of a climate gone awry. Yet from afar, it shines beautifully, a deceptive jewel cloaked in mystery. Next comes a world we know more intimately than any other. Earth, our home. Earth is the third planet from the Sun, situated in what's often called the Goldilocks zone, where temperatures are just right for liquid water. From space, Earth gleams blue and white, the blue of vast oceans and the white of swirling clouds. It is a world alive with water and wind, with continents and islands draped in green and brown and poles capped in white ice. In all our searching so far, Earth is the only planet known to host life, an astonishing abundance of life, from the deepest oceans to the highest mountains. Millions of species swim in its seas, walk its lands, and fly in its skies. Seen from afar, Earth's life announces itself in the very air. The oxygen we breathe is a byproduct of billions of plants and tiny organisms. For billions of years, Earth has been a canvas for life to evolve and thrive. Yet in the cosmic dance, Earth is just another planet orbiting a star, albeit one with a remarkable feature. It has beings who can contemplate the cosmos. If you were an alien traveler passing through our solar system, you might notice Earth by its unusual atmosphere or the glint of its oceans. Our planet is truly an oasis in space, a delicate, vibrant world where conditions aligned in just the right balance. By day, the sun's light nourishes our world. By night, Earth turns its face to the universe beyond, under the twinkle of the stars. It is easy to take for granted the miracle of our home, but set against barren neighbours like Mercury or Venus, Earth stands out as something very special indeed. Beyond Earth's orbit, we cross into colder realms. The fourth planet from the Sun is Mars, the red planet. From a distance, Mars has a distinct rust-orange hue, the colour of iron oxide, rusted iron dust, that covers its surface. Smaller than Earth, about half its diameter, Mars is a desert planet with a thin atmosphere of mostly carbon dioxide. The sky there is butterscotch-coloured during the day, tinted by fine dust, and pinkish at sunrise and sunset. Mars is cold now, bitterly cold at night, and generally dry. Yet Mars beckons with reminders of a warmer, wetter past. Dry river channels etch its surface, enormous canyons scar its face, and minerals tell us that long ago, liquid water flowed across Mars. There are polar ice caps of water ice and carbon dioxide ice that grow and shrink with the seasons. The largest volcano in the solar system, Olympus Mons, towers over the Martian landscape, a mountain about 3 times the height of Everest. And a chasm called Valles Marineris cuts across Mars's equator, a canyon system so long it would span the width of the United States, and so deep that Mount Everest would be lost within it. Today, no rivers run on Mars, and no lush plants grow. If life exists there now, it likely lurks hidden beneath the soil or in rare transient oases. But we suspect that eons ago, Mars might have had lakes, and maybe even seas, a thicker atmosphere, and a climate that could have supported life. Our robotic emissaries, rovers and landers, have been exploring Mars for decades, uncovering evidence of that lost era. Standing on Mars, you would see a rocky plain stretching to a ruddy horizon under a pale salmon sky, often hazy with dust. Mars is a world that once may have been a sibling to Earth in potential, now locked in a deep freeze, waiting perhaps for us to visit in person and uncover its remaining secrets. Past Mars, we leave behind the inner rocky planets. Between Mars and the next planet lies a wide belt of asteroids, millions of pieces of primordial rock orbiting the Sun. This asteroid belt marks a kind of boundary in the solar system. Beyond it, the planets swell into giants, huge worlds made mostly of gas and ice, quite unlike the small terrestrial planets of the inner solar system. Crossing that rocky frontier, we encounter Jupiter, the 5th planet from the Sun, and by far the largest. Jupiter is a colossal world, more massive than all the other planets combined. It's a gas giant, composed mostly of hydrogen and helium, the same elements that make up the Sun. But Jupiter never grew large enough to ignite as a star. Instead, it became a sort of failed star, shining not by its own light, but by reflecting the Sun's. If Earth is a pebble, Jupiter is a boulder by comparison. More than 11 Earths could fit across its diameter, and over 1,000 Earths could fit inside its volume. Its presence dominates the outer solar system. As we approach Jupiter, we see a banded sphere streaked with belts of white, tan, and rusty red clouds driven by fierce winds. Jupiter's atmosphere is turbulent and deep, a ceaselessly churning sky of ammonia clouds and immense storms. The most iconic feature is the Great Red Spot, a titanic storm twice the width of Earth that has raged for centuries. This giant vortex is like a cosmic hurricane. Jupiter has no solid surface in the traditional sense. If you descended through its clouds, the gas would grow denser and hotter, eventually transitioning into a strange hot liquid under crushing pressure. One remarkable thing about Jupiter is that it emits more heat than it receives from the distant sun. It still glows faintly in infrared, radiating leftover energy from its formation. Jupiter also has a subtle but immense magnetic field that traps charged particles, a gigantic magnetosphere that, if visible, would appear many times larger than the planet itself. For all its grandeur, Jupiter is also a caretaker of sorts. Its strong gravity shepherds many asteroids and comets, and it has likely pulled in or deflected objects that might otherwise threaten the inner planets, including Earth. In the darkness far from the sun, Jupiter stands as a mighty sentry and a jovial king of planets, living up to its name, Jupiter, or Jove, being the king of the Roman gods. Orbiting this giant is an entire miniature solar system, dozens of moons, from tiny asteroid-like rocks to immense moons the size of planets. 4 of these are especially large, the Galilean moons, and each of those is a fascinating world in its own right. We will visit the moons shortly. For now, we continue our outward voyage. Next in line, 6th from the Sun, is Saturn, the jewel of the solar system. Saturn is another gas giant, a bit smaller than Jupiter, but what it lacks in bulk, it makes up for in splendor. Encircling Saturn is an enchanting system of rings, broad, flat rings made of countless icy particles. Some are as small as grains of sand, others as big as boulders, all orbiting Saturn's equator in a thin, shining plane. From a distance, these rings make Saturn one of the most beautiful sights in the cosmos, like a golden globe adorned with a gossamer halo. The rings are not solid. They are a glittering swarm of ice and dust reflecting sunlight. Here and there within the rings, there are gaps, divisions sculpted by the gravitational dance of Saturn's many moons. Saturn itself is a pale golden sphere banded with subtle cloudy stripes, its features more muted than Jupiter's bold bands. It also has storms of its own. Saturn is less dense than water, which is a remarkable fact to ponder. Like Jupiter, Saturn has no solid ground, just atmosphere that grows thicker and hotter with depth. It too has a strong magnetic field and emits more heat than it receives from the sun. But it is those majestic rings that capture our imagination, evidence of delicate gravitational artistry at play. Perhaps they are the remnants of a shattered moon, or leftover material that never formed into one. Either way, Saturn's rings remind us that even destruction in the cosmos can create something of great beauty. Continuing outward, we come to Uranus, the 7th planet from the Sun. Uranus is an ice giant, smaller than Jupiter and Saturn, but still about 4 times the diameter of Earth. It has a tranquil blue-green colour when seen through a telescope, due to methane gas in its upper atmosphere absorbing red light and reflecting blue-green hues back to us. Uranus holds a special distinction. It is tilted dramatically on its side. Where Earth's axis tilts about 23 degrees, giving us moderate seasons, Uranus's axis lies over 90 degrees off vertical. Essentially, Uranus rolls around the Sun on its side like a barrel. This means that for part of its long 84-year orbit, one pole points almost directly at the Sun, bathing one hemisphere in continuous sunlight while the other is in prolonged darkness. Then, as Uranus moves along its orbit, the situation reverses. Such extreme seasons are unlike anything we experience. Why is Uranus knocked sideways? Perhaps long ago, a titanic collision toppled it. Despite this odd orientation, Uranus continues its journey calmly. It has a collection of thin, dark rings and over 24 known moons, adding to its mystique. From Uranus's great distance, the Sun is much dimmer than we know on Earth, yet it still shines as the central beacon keeping Uranus on its path. Finally, at the 8th planet, we reach Neptune, the outermost major planet of the solar system. Neptune is a deep blue world, similar in composition to Uranus, with an atmosphere rich in hydrogen, helium, and a trace of methane giving it that vivid azure color. Neptune is dynamic, with some of the strongest winds in the solar system, winds that can roar past 1,000 miles per hour, driving whirling storms in Neptune's skies. When Voyager 2 flew by Neptune in 1989, it spotted a dark storm the size of Earth swirling in the southern hemisphere. By the time we looked again years later, that storm had vanished and new ones had appeared. Neptune orbits the Sun at a distance of about 30 times Earth's distance. Here, the Sun is no longer a blazing disk dominating the sky, but rather a very bright star, a tiny, brilliant point giving off a pale daylight. Noon on Neptune might look more like early dusk to us. Sunlight takes over 4 hours to reach Neptune, compared to just 8 minutes to reach Earth. Around Neptune, a system of faint rings circles, and Triton, its largest moon, orbits in a backward, retrograde path, hinting that Triton might have been a captured object from the Kuiper Belt. Triton is unusual, almost certainly a wayward world snared by Neptune's gravity. It has a surface of nitrogen ice with a pinkish hue, and even shows evidence of active geysers, spraying nitrogen gas and particles into space. Because Triton orbits opposite Neptune's rotation, it is slowly spiraling inward. Eons from now, it may come close enough to be torn apart into a ring. For now, Triton remains Neptune's loyal, if unwilling, companion, a world with features reminiscent of Pluto, but bound to a giant planet. This, then, is the family of the Sun, a star at the centre, shining with nuclear fire. The inner rocky planets, Mercury, Venus, Earth, and Mars. The outer gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. And the far-flung dwarf planets, like Pluto, on the solar frontier. Each world is unique. An explorer could spend a lifetime on any one of them and still have more to discover. Yet they all share a common origin and travel the same cosmic highway around our star. Together, they paint a portrait of what a solar system can be, from the furnace-like heat near the Sun to the frozen darkness beyond Neptune. As we drift away from Neptune and Pluto, looking back toward the Sun, we see a faint glow encompassing the space in between. That glow is the combined light of countless small particles and bits of debris scattering sunlight. A reminder that the solar system is not empty void, but a place filled with dust, ice, and rock along with the planets. The Sun's gravity holds all of this together, orchestrating the movements of every planet and pebble. And while the planets themselves are the major worlds, they are not alone. Circling many of them are smaller companions, moons of all shapes and sizes, as varied as the planets they accompany. These moons are the next part of our journey, for they too carry wonders. Some dance as tiny specks around their parent planet, while others are large enough to have skies and geological dramas of their own. On any clear night when the moon is out, its gentle light bathes the world in a silver glow. This glow is not the moon's own. Our moon is a barren sphere of rock, shining only by reflected sunlight. Yet for us on Earth, moonlight has a special magic. It softens the darkness and invites quiet contemplation. Since ancient times, the moon has been our companion in the sky, waxing and waning through its phases each month, its changing shape a natural calendar. We have given it many names and stories. We have measured time by its cycles. The moon's presence has subtly shaped life on Earth. Its gravitational pull causes the tides to rise and fall, a rhythmic breathing of the oceans that may have helped life move from sea to land eons ago. It also acts as a stabilizer for Earth, keeping our planet's tilt and seasons relatively steady over long ages. It is hard to imagine our nights without the moon's familiar face. Up close, Earth's moon is a silent, ancient world. Its surface is covered in fine dust and punctuated by craters from meteor impacts. Dark lava plains form the man-in-the-moon patterns we see from Earth. There is no air, no sound, and no flowing water. Nothing but stark sunlight and shadow. When the sun shines on the lunar surface, the ground becomes searing hot. At night, it plunges to brutal cold. The sky from the moon is pitch black even when the sun is up. And when the sun sets, the stars come out by the millions, unblinking in the airless void. If you stood on the moon and looked up, you would see Earth hanging above the horizon, a blue and white marble 4 times the apparent size of the moon in our sky. Earth would shine brilliantly, a beacon of colour and life in the darkness, going through phases just as the moon does for observers on Earth. To see an Earthrise from the moon, our planet cresting above the lunar horizon, is to witness a breathtaking sight. Only a few human eyes have seen that directly, but photographs have shared its beauty. A fragile, glowing Earth suspended in the black sky above a desolate lunar landscape. It's a scene that can leave one humbled, filled with both awe and a quiet sense of loneliness. The moon is just one of many such companions in our solar system. It is unique to us, but other planets have moons of their own, some even more impressive or intriguing than ours. Interestingly, the 2 planets closest to the Sun, Mercury and Venus, have no moons at all. Mercury is too close to the Sun's gravity to hold on to one. Any moon would likely crash into Mercury or be pulled into the Sun. Venus, for reasons still not fully understood, also travels alone. But beyond Earth, every other planet has an entourage. Mars, our neighbour, has 2 tiny moons, Phobos and Deimos. Unlike our large moon, these are little potato-shaped rocks, likely captured asteroids. Phobos, the larger one, about 22 kilometers across, orbits Mars so closely that it whips around the planet in just about 8 hours, faster than Mars rotates. In Mars's sky, Phobos rises in the west and sets in the east, completing multiple trips across the sky in a single day. It appears only about 1/3 the width of our moon and moves noticeably over a few hours. Deimos, even smaller, looks more like a bright star, a mere point of light. These diminutive moons are dark, carbon-rich bodies, heavily cratered. In tens of millions of years, Phobos may spiral inward and break apart, perhaps forming a temporary ring around Mars before its fragments fall. For now, these little moons keep Mars company, occasionally casting tiny shadows on the rust-red surface as they transit the Sun. When we venture out to Jupiter, we enter a realm teeming with moons. Jupiter has nearly 100 known moons, a true miniature solar system. 4 of them, the Galilean moons, are so large and bright that Galileo saw them with his small telescope over 4 centuries ago. These four, Io, Europa, Ganymede, and Callisto, are each a unique world. Io, closest to Jupiter, is a world of fire and brimstone. It is the most volcanically active body in the solar system. Its surface is mottled with sulfur yellows, oranges, and blacks from constant eruptions. Dozens of volcanoes dot Io, some blasting fountains of lava and gas miles high. Jupiter's immense gravity and the tugs of the other moons flex Io like a stress ball, heating its interior through friction. The result is a constantly erupting landscape. If you could hover above Io, you'd see lava lakes and glowing rivers of molten rock. Above, Jupiter would loom huge in the sky, perhaps 20 times the apparent diameter of our moon, striped and immense. It must be an awe-inspiring sight, a gigantic planet hanging overhead while the ground rumbles with volcanic fury. Next out is Europa, a smooth, bright moon, slightly smaller than Earth's moon. Europa is covered by a shell of ice, and beneath that ice lies a hidden ocean of liquid water. Its surface is crisscrossed with long, dark cracks and reddish streaks where the ice has fractured and perhaps vented material from below. Europa's icy crust is young and active, continually resurfaced by forces from beneath. Occasionally, plumes of water vapor have been detected erupting from Europa's surface, geysers from the ocean below punching through. Europa is one of the most tantalizing places in the solar system, because where there is liquid water, energy, and the right chemistry, there could be life. In the dark ocean beneath Europa's ice, warmed by tidal heating, and perhaps mineral-rich from the sea floor, life might exist in forms we can only imagine. Someday, we may drill through that ice, or send a submarine probe to explore Europa's ocean and finally learn if it harbours living creatures in its cold depths. Then there is Ganymede, the giant among moons. Ganymede is the largest moon in the solar system, bigger even than Mercury. It's a world of rock and ice, with a surface marked by both dark, ancient craters and lighter, grooved regions where some past activity has reshaped the landscape. Ganymede may also hide a deep ocean beneath its ice, sandwiched between layers of frozen crust. Callisto, the fourth Galilean moon, lies farther out. Callisto is a heavily cratered ball of ice and rock, seemingly frozen in time with an ancient surface that has changed little over billions of years. It's like a cosmic time capsule, its face still bearing the scars of the solar system's early days. Callisto, too, might have a slushy ocean deep inside, hinted at by subtle magnetic readings, showing that even a seemingly dead moon could hold a secret sea within. Jupiter's lesser moons range from small asteroid-like chunks, only a few kilometers across, to irregular captured objects in distant orbits. They whirl around Jupiter in a complex dance. Some orbit in the same direction as the big moons, others backward, likely captured comets or asteroids now bound to Jupiter's gravity. In total, Jupiter's retinue forms a rich system of worlds orbiting a world. Saturn, too, is accompanied by a great many moons. More than 80 are known so far, with more still being discovered. The largest is Titan, and Titan is extraordinary. Titan is second in size only to Ganymede, and even larger than planet Mercury. What sets Titan apart is its thick atmosphere. Titan has a dense, orange-coloured atmosphere, mostly of nitrogen, with a touch of methane. This atmosphere completely hides the surface from view. For a long time, Titan was a mystery, but we now know it has a complex and strangely Earth-like geography hidden under those clouds. Titan is so cold, around 290 degrees, that water is as hard as rock, but methane exists as a liquid. Titan has rivers and lakes of liquid methane and ethane, especially near its poles. It even has a weather cycle. It rains methane, has clouds, and perhaps occasional methane thunderstorms. When the European probe Huygens landed on Titan in 2005, it found damp sand and pebble-sized chunks of water ice on a frigid floodplain. The landscape had drainage channels carved by liquid methane. If you stood on Titan's surface, you'd feel a dense, foggy air around you, an orange twilight gloom. The sun would be a small, hazy spot. Overhead, if the clouds parted, Saturn's huge form might be dimly visible, with its rings spanning the sky. Titan intrigues scientists because its chemistry, rich in organic molecules, might resemble a deep frozen version of what Earth's chemistry was like before life began. Could some form of simple life exist in Titan's liquid hydrocarbon lakes, or maybe far below its surface? It's a long shot, but Titan shows us how diverse and surprising moons can be. Among Saturn's many other moons, one more steals the spotlight: Enceladus. Enceladus is tiny, only about 500 kilometers across, but brilliantly reflective like fresh snow. Its icy surface shines almost pure white, crisscrossed by subtle blue cracks. At Enceladus's south pole, huge geysers of water vapor and ice crystals continuously erupt from long fissures nicknamed tiger stripes. These plumes shoot material into space and actually create one of Saturn's rings, the diffuse E-ring. The discovery of these geysers by the Cassini spacecraft was a revelation. It told us that Enceladus, like Europa, has a liquid water ocean beneath its ice. Heat, generated by tidal flexing due to Saturn's gravity, keeps this ocean from freezing solid. Along with the water in the plumes, Cassini detected organic molecules and tiny grains of rock, suggesting hydrothermal vents on an ocean floor below. Enceladus has the necessary ingredients for life: water, chemistry, and energy. A tiny moon that looks like an ice ball turned out to be a dynamic world, with perhaps one of the most habitable environments, for microbes at least, beyond Earth. Flying through those geysers, we essentially sampled an extraterrestrial ocean. Future missions may return to delve deeper into Enceladus's secrets, perhaps even searching for direct signs of life in its ejected spray. Saturn's collection of moons doesn't end there. There is Iapetus, half as bright as snow on one side and as dark as coal on the other, with a puzzling equatorial ridge like the seam of a walnut. There is little Mimas, with a crater so large it gives it a passing resemblance to the Death Star from fiction. Dozens more, each a frozen fragment with its own orbit, complete the tapestry of Saturn's system. Some moons, called shepherd moons, herd the edges of Saturn's rings, their gravity helping to keep the ring particles in line. Each moon adds its own chapter to Saturn's story. Moving on to Uranus, we find that even this distant, tilted planet has a family of moons, though smaller and fainter ones. Uranus has 5 major moons and a slew of smaller ones. The largest are Titania and Oberon, named for Shakespearean characters. Uranus's moons are uniquely named after fairies and spirits from literature. These moons are dark, icy bodies with ancient cratered surfaces. One of Uranus's moons, Miranda, is particularly bizarre. It looks almost patchwork, with immense canyons, terraces, and regions that seem jumbled together. It's as if Miranda was shattered and haphazardly put back together. Cliffs on Miranda soar to heights of 20 kilometers. This moon's strange geology hints at violent impacts in its past. All of Uranus's moons orbit around the planet's equator. So given Uranus's sideways tilt, the moon's orbits are tilted along with it. They likely experience the same extreme seasons as Uranus, with decades of sunlight followed by decades of darkness at the poles. Neptune's crowning moon is Triton. Triton is unusual among large moons because it orbits opposite to Neptune's rotation and at a tilt, clearly marking it as a captured object, not one that formed with Neptune. It might have been an independent icy world like Pluto that strayed too close and was snared. Triton has a surface of frozen nitrogen with a pale pinkish tint. When Voyager 2 flew by, it observed dark geysers erupting from Triton's surface, nitrogen gas carrying dark particles up into the thin atmosphere, then drifting downwind as streaks on the surface. Triton, despite the frigid temperature only a few dozen degrees above absolute zero, is geologically active. It even has a thin atmosphere, mostly nitrogen like Earth's, but so thin you'd barely notice it. Triton's fate is sealed. Its backward orbit means that, over many millions of years, it is spiraling inward. One distant day, Neptune's gravity may pull Triton apart, possibly creating a new ring. For now, Triton remains an intriguing moon with a paradoxical combination of features, part Pluto-like ice world, part active geology, circling a blue giant planet. Even beyond Neptune, Pluto and its companions have moons. Pluto's moon, Charon, is so large relative to Pluto that some consider them a double dwarf planet system. Charon's gravity is strong enough that Pluto and Charon orbit a point in space between them, like two dancers holding hands and spinning around a shared center. Charon itself has huge canyons and a reddish cap at its north pole, possibly stained by gases escaping Pluto. Pluto also has at least 4 small moons: Styx, Nix, Kerberos, and Hydra, tiny irregular bits of ice caught in the complex gravitational dance of Pluto and Charon. These moonlit companions throughout the solar system are more than mere satellites. Many are worlds with their own atmospheres, climates, and internal heat. They teach us that a planet isn't a solitary entity. It's often the hub of a mini-system. Our exploration of these moons has only just begun, but already they have reshaped our understanding of what a habitable environment might be. We once thought only a planet in the just right zone around a star could have liquid water and the potential for life. Now we see Europa and Enceladus, far from the sun's warmth, hiding warm oceans beneath ice. Titan, in the outer darkness, has lakes and weather of liquid methane. Our own moon taught us what it's like to walk on a world beyond Earth, and how stark and beautiful a lifeless landscape can be. In the soft glow of the moonlight we know so well, it is easy to forget that countless other moons are out there, each with its own story. They accompany their planets through space as faithful attendants, sometimes even stealing the show. The next time you look up at our moon and see it shining, remember it is just one of many moons. Each has its own wonders, and together they enrich the grand tale of our solar system. Beyond the moons, there are yet smaller wanderers roaming the solar system. Not planets, not moons, but drifters that travel on their own paths. The comets, the asteroids, the meteoroids. These are the cosmic wanderers, the leftovers from our solar system's formation. They are pieces of raw material, or perhaps visitors from other stars, and they too have tales to tell. Our journey now turns to these little travelers, the cosmic wanderers that sometimes pay Earth a visit, or even carry the seeds of life across the stars. Throughout our solar system, and far beyond the orbits of the planets, drift countless smaller wanderers. They are fragments of creation, bits and pieces that never formed into large worlds. Some are rocky, some icy, all ancient. They roam the space between the planets and occasionally pay our world a visit in spectacular ways. In the vast gap between Mars and Jupiter lies the asteroid belt, a sprawling collection of rocks and boulders orbiting the Sun. These asteroids range in size from the dwarf planet Ceres, nearly 600 miles across, down to pebbles. They are remnants of the early solar system, building blocks that never coalesced into a planet, perhaps due to Jupiter's disruptive gravity. Most asteroids in the belt quietly circle the Sun, each far from the next, despite what movies might show. A spaceship flying through the belt would mostly see emptiness, with a distant rock here or there. Still, there are millions of asteroids out there. Occasionally, gravitational nudges send one on a new course. Some asteroids wander inward toward the Sun and cross Earth's orbit. These near-Earth asteroids are watched carefully by astronomers today, for we know that in the past, some have collided with our planet with drastic consequences. About 66 million years ago, a large asteroid, roughly 6 miles across, struck Earth and ended the age of the dinosaurs. The impact blasted debris high into the atmosphere, shrouding the world in darkness and cold. It was a catastrophe, but also an opportunity. With the giants gone, our mammal ancestors flourished, eventually leading to us. It's a sober reminder that even a small cosmic wanderer can change the course of life on Earth. Thankfully, such large impacts are rare. Far more common are tiny messengers from space, meteoroids that streak into our atmosphere. When you see a shooting star, it's usually a piece of cosmic dust or a pebble, burning up in a brilliant flash as it plummets through the air at tens of thousands of miles per hour. For a brief moment, it creates a glowing streak that can take your breath away, a little gift from the cosmos, gone in the blink of an eye. Every so often, Earth passes through the dusty trail left by a comet, resulting in a meteor shower. On those nights, dozens of shooting stars might grace the sky each hour. Each meteor is a tiny fragment of a comet's tail, incinerating as it meets its fiery end in our atmosphere. If any piece is large enough to survive and reach the ground, it becomes a meteorite. People have been finding meteorites for thousands of years, sometimes not realizing their origin. An unusual stone that legend might claim fell from a god. Today we study meteorites with scientific tools, and they tell us of the solar system's youth. Some meteorites are pieces of Mars or the Moon, blasted off those worlds by impacts and eventually falling on Earth, delivering rocks from those distant places. Others are chunks of primitive material from when the Sun and planets were forming, containing grains that are older than Earth itself. Remarkably, some meteorites carry amino acids and other complex organic molecules. These molecules, the building blocks of life, formed in space, in the cold molecular clouds between stars, long before our Sun existed. Imagine that. Ingredients for life created in interstellar space, hitchhiking on comets and asteroids, and raining down on the young Earth. It's tantalizing to think our planet may have been seeded with the raw materials of life by these wandering messengers. In fact, a famous meteorite from Mars caused excitement in the 1990s when scientists thought they saw microscopic fossils in it. suggestive of ancient Martian life hitchhiking to Earth. That finding is still debated, but just the possibility casts cosmic wanderers in a new light. Not only can they reshape planets, they might connect life from one world to another. Not all wanderers are rocky. Some are icy nomads from the outer reaches, the comets. Comets are often called dirty snowballs, mixes of ice, water ice, frozen gases like carbon dioxide and carbon monoxide, and more, and dust, compacted together. Most of their lives they dwell in deep freeze far from the sun. But when a comet ventures into the inner solar system, the sun's warmth begins to vaporize its ices. The comet springs to life, developing a glowing coma, a tenuous atmosphere of gas and dust around the nucleus, and one or more magnificent tails. One tail is made of ionized gases, pushed straight away from the sun by the solar wind, often glowing bluish. The other tail is made of dust particles that lag behind the comet's trajectory, reflecting sunlight, and often appearing white or yellow and curving gently. These tails can stretch millions of miles into space, making comets some of the most dramatic objects in the sky. To us on Earth, a bright comet is a sight of rare beauty. Suddenly there is a fuzzy star with a shimmering tail, hanging in the twilight or dawn. It's no surprise that before their nature was understood, comets were seen as omens, portents of change or doom sent by the gods. One of the most famous comets is Halley's Comet, which returns to our neighbourhood roughly every 76 years. It has been observed since antiquity. It was recorded by Chinese astronomers and famously appeared in 1066, reportedly seen as an omen before the Battle of Hastings. It's even embroidered in the Bayeux tapestry. Halley's Comet last visited us in 1986, when spacecraft got their first close look at its dark, potato-shaped nucleus, venting jets of gas and dust. It will come again in 2061, a reminder that, for all our modern knowledge, we still await these cosmic visitors, much as our ancestors did. Comets come from two main reservoirs. Short-period comets like Halley likely originate in the Kuiper Belt, a ring of icy bodies beyond Neptune, of which Pluto is a member. Long-period comets hail from the distant Oort cloud, a vast spherical shell of icy objects perhaps a quarter of the way to the nearest stars. A long-period comet may spend thousands or even millions of years in the dark before the random nudges of passing stars send it plunging toward the sun for a brief, glorious appearance, never to return in our lifetimes. Comets have likely played a crucial role in Earth's history. In the early days of the solar system, frequent impacts by comets may have delivered a significant portion of Earth's water and organic compounds, helping to set the stage for life. Even now, we find that comet dust contains complex carbon molecules. When the European spacecraft Rosetta orbited comet 67P Churyumov-Gerasimenko in 2014 and landed a probe on it, scientists found organic molecules in the comet's halo. This supports the idea that comets seeded the young Earth with the building blocks of life. It also implies that these building blocks, amino acids, nucleic acids, sugars, are likely everywhere, drifting between the stars on comets and grains of dust, ready to fertilize any hospitable world. As we search the skies, we sometimes find something truly unexpected. Wanderers that come from outside our solar system entirely. In 2017, astronomers spotted an object moving so fast and on such a peculiar trajectory that it could only have come from another star. This visitor was named Oumuamua, a Hawaiian word meaning scout from afar. It was small and faint, detected only after it had already slingshotted around the sun and was heading back out to interstellar space. Oumuamua had no coma or tail, but its motion hinted that it might have expelled some material like a comet, perhaps in a way we couldn't see, giving it a slight acceleration. Its shape was hard to determine, but it seemed extremely elongated or flat, a truly bizarre object. Its true nature remains a mystery. It could have been a fragment of an icy planetesimal from another solar system, flung out during planet formation and wandering the galaxy for eons before happening upon us. In 2019, a second interstellar visitor was discovered. A comet, later named Borisov, clearly sporting a tail. Unlike Oumuamua, this one looked and behaved like a familiar comet, except that its path showed it was just passing through, not bound to the sun. These interstellar interlopers confirm that the space between stars is not empty. Pieces of other solar systems do drift among the stars. One can imagine that over the history of the galaxy, countless rocks and comets have exchanged between star systems, perhaps even carrying microbial life spores hitchhiking across light years, an exotic but intriguing idea. All these wandering objects, asteroids, comets, meteors, and interstellar vagabonds, form bridges between worlds. They are messengers carrying information about distant places and times. We have learned to read their messages. By studying meteorites, we learn about the birth of the solar system. By sampling comet dust, we discover complex organic chemistry at work. By tracking near-Earth asteroids, we uncover the history of impacts on our planet, and perhaps avert future ones. They also remind us that the solar system is not a static, clockwork arrangement of planets alone, but a dynamic environment where big and small worlds interact in an ongoing story. Jupiter's gravity flings comets inward, the sun's heat shatters them, Earth sweeps up their dust. On certain nights, when you see a meteor flash or a pale comet gliding through the sky, you are witnessing this grand cosmic exchange. It can be humbling to realize that something as fleeting as a shooting star is actually a message from outer space, a tiny fragment of an asteroid or comet that traveled for billions of miles before ending its journey in our atmosphere as a momentary streak of light. And while we humans have begun sending our own emissaries, spacecraft, beyond our home planet, nature has been sending emissaries for eons in the form of these wanderers. As we follow these small travelers outward to the fringes of our solar system, we reach the very boundary of the sun's influence. The comets that originate in the Oort cloud mark that boundary, a distant repository of icy bodies nearly a light year away. This cloud of comets is like a deep reservoir of potential wanderers, defining the outer edge of our solar neighborhood. Beyond those solar shores, we truly enter interstellar space, the ocean of darkness between the stars, sprinkled with the faint light of far-off suns. Humanity's farthest probes are just now crossing into that realm. It is the next frontier on our journey, leaving behind the last grasp of our sun's gravity and venturing into the space between the stars. What lies beyond, in that vast unknown? To find out, we must say goodbye to our familiar solar system and set sail on the cosmic ocean of the Milky Way. Our voyage now carries us beyond the solar shores and into the interstellar deep. The edge of our solar system is not a sudden cliff or a visible wall, but a gradual fading of the sun's presence. As we venture farther out, the solar wind, a stream of charged particles blowing outward from the sun, grows weaker and thinner. Eventually, around 11 billion miles from the sun, even that wind yields to the pressure of the sparse gas between the stars. This is the heliopause, the boundary of the heliosphere, essentially the outer bubble of the sun's influence. Beyond it lies interstellar space, the realm between the stars. In 2012, Voyager 1, a spacecraft launched in 1977 when Disco was young and before many of us were born, crossed that boundary and became the first human-made object in interstellar space. Its twin, Voyager 2, followed in 2018. Each carries a golden record packed with sounds and images of Earth, music, birdsong, greetings in many languages, a friendly time capsule cast into the cosmic sea, with the faint hope that someday it might be found by other beings. Out here, more than 15 billion miles from Earth, the Sun is just another bright star in the sky. If you were riding with Voyager 1 and looked back, you would no longer see the planets as distinct points. Even mighty Jupiter would have vanished in the Sun's glare. Our Earth, that vibrant blue oasis, would be utterly invisible to the naked eye. In 1990, as Voyager 1 was departing the solar system, it turned its camera back toward home at the request of astronomer Carl Sagan. It took a photograph of Earth from a distance of about 4 billion miles. In that image, Earth is just a tiny speck of light, a pale blue dot against the blackness of space, caught in a lens flare from the Sun. All of human history, every hero and villain, every joyful and sorrowful moment has taken place on that mote of dust suspended in a sunbeam. Reflecting on that image, one can't help but feel both humbled by our smallness and uplifted by the fact we are part of something so vast. Now our journey carries us truly beyond the solar shore. We drift in interstellar space, the space between stars. What is it like here? It is emptier than any vacuum we can create on Earth, yet not completely void. There are a few stray atoms per cubic centimetre, mainly hydrogen, the ghost of ancient star atmospheres and the raw material for future stars. There are high-energy cosmic rays zipping through, charged particles from distant supernovae. There are faint wisps of nebulae, enormous but tenuous clouds of gas and dust that we might pass through from time to time. It's cold, just a few degrees above absolute zero, and dark. If our ship had windows, we would see the Milky Way as a dense band of stars wrapping around us, since we're now looking at it from within, but without the sun's bright glare. The familiar constellations would look nearly the same as from Earth, for we haven't gone far enough to significantly change our perspective on them, though over many millennia those patterns would subtly distort as we moved light years away. The nearest star to our Sun is Proxima Centauri, part of a triple star system, along with Alpha Centauri A and B. Proxima is a dim red dwarf, invisible without a telescope, but it holds a special interest. It has at least one planet in its habitable zone. That planet, discovered in 2016, is only slightly more massive than Earth. It's tantalizing to think such a world orbits our closest neighboring star. Yet close, in cosmic terms, is still so very far, over 4 light-years away, which is about 25 trillion miles. A light-year is the distance light travels in a year, nearly 6 trillion miles, or about 9.5 trillion kilometers. At the speeds our fastest probes currently travel, it would take tens of thousands of years to reach even Proxima Centauri. For now, the prospect of visiting is far beyond our reach. But in our mind's eye, we can picture it. A tiny star with a possibly Earth-like planet, just over the horizon of our knowledge. Out here in interstellar space, we have to adjust to a new sense of scale. Distances are measured in light years, and travel times in centuries or millennia. If you feel a sense of loneliness thinking about this emptiness, remember that the emptiness is not truly empty. It's filled with the gravitational influence of the galaxy's billions of stars, and with the diffuse remnants of those stars' life cycles. And we ourselves are made of material that was once part of this interstellar medium. Before the sun formed, the atoms that make up our world and our bodies were adrift in space. In a very real sense, we are returning to our broader home, the galaxy that birthed our sun and gave substance to our being. As we float between the stars, we can look around and see our galaxy from within. The Milky Way is a barred spiral galaxy about 100,000 light-years across. Our sun is situated in a spiral arm called the Orion Arm, roughly 26,000 light-years from the galactic center. From where we are, the center of the galaxy, in the direction of the constellation Sagittarius, appears as a bulge densely packed with stars. In that direction, hidden behind clouds of dust, lies a supermassive black hole around which our entire galaxy revolves. If we look outward from the center toward the edge of the galaxy, the stars thin out, and beyond them lies intergalactic space, another leap into even greater emptiness. But that is a journey for another time. For now, imagine taking a moment to simply drift. Turn off the engines of our imagination ship and float in silence. The nearest sun is a distant point of light behind us. The next nearest sun is a distant point ahead. All around, the sphere of the night, with its myriad stars, surrounds us like an eternal, silent cathedral. The combined light of countless distant stars provides a dim glow. We are far from any warmth, but not far from wonder. Our sun, now behind us, would appear as just one more star in the constellation Cassiopeia, perhaps, since from an alien sky, our familiar constellations would change shape. Somewhere in the direction of that sunstar is everything we know, every person, every tree, every ocean. Such a perspective can bring feelings of isolation, but also a profound clarity about what matters. Out here, one realizes that all of humanity is in the same little boat, Earth, in a vast sea. That awareness can foster a sense of unity and guardianship for our home. Even in this far darkness, though, we do not feel completely alone. The light of the stars is with us, and with that light comes the certainty that there are other suns, other possibilities. We now know that planets are common. In the past quarter century, astronomers have discovered thousands of exoplanets, planets around other stars. They've found gas giants hugging their stars, icy worlds, rock worlds, even some that might be temperate and Earth-like. Statistically, most stars likely have planets. The night sky is no longer just stars, it's filled with other solar systems. When we peer up at the stars from Earth, or from our imaginary ship, we can wonder, is anyone on a planet circling one of those stars, looking back at us? The sheer number of worlds out there makes it hard to believe that Earth is the only one with life, though we have yet to find evidence of neighbours. Perhaps life is rare, or perhaps the distances are just too great. But the possibility that we are not alone lingers in the quiet of space. If we were truly on a starship journey now, having left our sun behind, our next target might be one of those nearby stars, like Alpha Centauri. Perhaps many centuries hence, explorers will embark on that voyage, for real. For now, we send our minds and our robotic scouts. One day, far in the future, maybe descendants of humanity will stand on a planet around another sun and look up at an alien sky with unfamiliar constellations and point out a particular star that is our sun and marvel that their ancestors came from so far away. At this point in our journey, we have left our solar cradle. We are crossing the threshold into the wider universe. It's akin to an ocean explorer leaving sight of shore. The comfort of the familiar recedes, and only the endless sea lies ahead. But we carry with us knowledge and curiosity as our compass and sail. Even if our physical forms remain on Earth, through our intellect, we have already ventured far beyond. Our telescopes are like ships for the mind, bringing into view planets and stars and galaxies we could never reach by foot. Through them, we've stood on the shores of alien seas on Europa, vicariously via space probes, flown through Saturn's rings, and glimpsed the light of galaxies billions of light years away, which left those galaxies before Earth itself had formed. The darkness between stars is not something to fear, but something to wonder at. It is the canvas on which the universe is drawn. Across it, nature has scattered wonders, clouds of gas that glow pink and blue where new stars are being born, the remnants of supernova explosions expanding outward, maybe even the signals of distant civilizations, though we haven't detected them yet. We listen and we watch, hoping one day to find we are not the only storytellers in this cosmic ocean. For now, as part one of our journey comes to a gentle close, we find ourselves coasting through interstellar space with the sun, just another point of light behind us. This is a natural pause, a place to stop and reflect before we press on. We have travelled from Earth's grasslands under ancient stars, past all the planets and moons of our solar system, and now out into the great beyond. In our imagination, we have covered billions of miles and untold years of history. And yet, in the scale of the cosmos, we have only just stepped off our front porch. The journey through the cosmos is far from over. In fact, it is only just beginning. Ahead of us lies the glittering expanse of the Milky Way galaxy, with its billions of stars and countless mysteries. Beyond that, the realm of other galaxies and the large-scale structure of the universe, and questions of where it all began. All that awaits in the chapters to come. For now, we float in the starlight, carrying the knowledge that we have gained so far, and the anticipation of what lies ahead. The cosmic ocean stretches out infinitely in all directions, and we, tiny and curious, will continue our voyage. Let us take a deep breath in this peaceful darkness, savor the wonder of how far we've come, and prepare to journey onward, to explore the next reaches of this breathtaking cosmos. The stars are calling, and we will answer. The journey continues. Drifting through the silent void of space, we find ourselves amid an immense cosmic cloud. It is a dark nebula, a vast, obscuring veil of gas and fine dust, so cold and diffuse that it barely emits any light of its own. From a distance, it appears as a shadow against the starry background, a black silhouette where starlight is blocked. Yet inside this quiet darkness, hidden from our eyes, something wondrous is unfolding. In these opaque clouds, the seeds of new stars are gathering and coming alive. Within the nebula's depths, gravity is gently at work. Over countless years, delicate tendrils of gas begin to coalesce, drawn together by their own faint pull. Here and there, slight ripples and eddies cause gas to pile a little denser. Perhaps a distant supernova's shockwave once passed through this cloud, stirring and compressing it in places. Perhaps two clouds collided, or maybe a random whisper of chance nudged a region to collapse. Whatever the trigger, patches of this cloud are now falling inward under gravity's ancient spell. As we drift further in, we realize that what once seemed empty is actually teeming with structure. Dense knots of matter are forming, each one a potential new star. These clumps, called protostellar cores, grow slowly but relentlessly. Gas and dust swirl into them, the cloud's sparse material drawn to any growing concentration, like moths to a flame. The process is gradual, measured in tens of thousands to millions of years. A timescale beyond human reckoning, yet just a heartbeat in cosmic time. In these embryonic stellar wombs, gravity's gentle squeeze raises the pressure and temperature bit by bit. In the heart of one such contracting clump, atoms are pressed closer and move faster as the core heats up. What began as a cold, dark fragment of a nebula begins to glow faintly with its own warmth. This is a protostar now, not yet a full-fledged star, for true starlight from sustained fusion has not ignited, but a newborn star in the making. It remains cocooned in layers of infalling gas, hidden deep in the cloud. If we could see it with special eyes, perhaps in infrared light that penetrates dust, we would make out a warm ember forming at the center of a swirling haze. Material continues to rain down onto the protostar, building it up. Some of the infalling gas forms a whirling disk around the newborn star, like a spinning skirt of cosmic matter. Within that disk, countless tiny dust grains collide and gather, the first steps toward forming planets that might one day circle the star. But for now, the protostar continues to feed on the surrounding gas. Occasionally, it gulps down more material than it can handle smoothly. The excess is expelled as twin jets of hot gas shooting out along the star's poles. These jets pierce through the cloud, announcing the star's quiet birth with narrow beams of energy that light up the nebula's insides. Where these jets crash into the surrounding gloom, they heat the gas and make it glow. Bright, fleeting patches of nebulous light appear at those collision points, signposts of a star's arrival that briefly illuminate the darkness before fading again into the mist. All around us, in this stellar nursery, multiple stars are being born together. Dozens, perhaps hundreds of protostars are taking shape within the same giant cloud. Often, they form in clusters, sibling stars sharing the same birthplace. In many cases, stars are born not alone, but in companionship. Pairs or triplets of stars may emerge together, bound in orbit around each other. Astronomers even suspect that most stars start out with a partner star, a twin born from the same clump of gas. Our own sun may have had a sibling star in its youth, sharing its cradle before drifting away over billions of years. In these nurseries, such family groups of stars are common, as gravity and chance weave multiple stellar lives out of one cloud. Slowly but surely, the central protostar grows denser and hotter. When the core temperature climbs to millions of degrees, a profound change occurs. The atoms at its center, mostly hydrogen, are moving so fast and are packed so tightly that they begin to fuse together. 4 hydrogen nuclei merge into one helium nucleus, and in that alchemy, a tiny bit of mass is transformed into a tremendous amount of energy. This is the spark of starlight, the moment a protostar becomes a true star. At first, the newborn star's light struggles to emerge. It must fight its way out of the cocooning gas and dust that still surrounds it. Gradually, the radiance pushes away the shroud that has fed it for so long. The surrounding nebula, once dark, now glows softly, tinted in pinks and blues as the star's energy excites the hydrogen and other gases around it. What was once an opaque, lightless patch of cloud begins to shine as a beautiful luminous haze. The star has announced its arrival. Imagine the scene as we hover amidst this nursery. Starlight filters through gauzy curtains of cosmic dust. We see great billowing shapes, towers and pillars of denser gas, sculpted by the light and winds of newborn stars. Each pillar may hide new baby stars forming within it, like cosmic stalagmites sheltering embers at their tips. In places, the veil has opened to reveal clusters of bright young suns that have already cleared out cavities around themselves. The Orion Nebula, a real stellar nursery visible even with small telescopes from Earth, offers just such a view. Hundreds of newborn stars lighting up a cavern carved from the gas that created them. The Pillars of Creation, another nursery within the Eagle Nebula, stand as silent monuments to this process. Finger-like columns of gas and dust, riddled with fledgling stars at their tips, slowly eroding under the onslaught of intense starlight from nearby newborn giants. In time, the balance in the nursery shifts. The fresh star's radiation and stellar winds push away the remaining shreds of their birth cloud. The nursery that once nurtured them becomes dispersed by the very children it brought forth. What remains of the nebula may form a faint haze around the new star cluster, or be blown completely into interstellar space, seeding the galaxy with enriched gas for future generations of stars. The infant stars, once hidden together in the womb of the nebula, are now exposed to the wider cosmos, shining as a collective jewel box of lights against the dark. We drift through one such newborn cluster. Perhaps these stars will remain bound together by gravity for a time, dancing slowly around a common center as an open cluster for hundreds of millions of years. The sky around us is alive with their youthful glow, many of them hot and blue-white, shining fiercely after their turbulent birth. Others are cooler and smaller, glowing with a gentler golden or reddish light. Each carries within it the precious gift of radiance, the result of nuclear fusion burning steadily in its core. Not far from some of these young stars, we find disks of leftover gas and dust encircling them. In these disks, countless microscopic grains are quietly sticking together. Over millions of years, those grains may clump into pebbles, then rocks, then mountain-sized boulders. Eventually, they can assemble into new worlds, orbiting their young suns. The faint beginnings of planets are a natural part of this stellar birth environment. Someday, these stars might be attended by full families of planets, perhaps even some that harbour life. But those chapters of the story are still to come. For now, in this moment, the chaos of birth is giving way to calm. The nursery has done its job, and where once there was darkness, there are now stars. The once cold gas is warmed by starlight. The hush of space is broken by the gentle winds flowing from the young suns and the occasional flare of a star adjusting to its new life. Within a few million years, mere instants on cosmic scales, this nursery will have completely transformed. The dramatic pillars and thick clumps will have dissipated, blown away by the energy of the cluster's stars. What will remain is a new grouping of stars peeking out into the galaxy, ready to begin their long journeys through time. It's humbling and wondrous to think that our own sun once emerged from such a nursery. More than 4.5 billion years ago, before Earth existed, the sun was just another protostar forming in a dusty nebula. It likely had sibling stars born alongside it, a whole cluster of brothers and sisters that gradually drifted apart as they orbited the Milky Way. The atoms that make up our planet, and even our bodies, were forged in earlier generations of stars, long before the sun. Those stars lived and died, dispersing their enriched guts into the nebula that became the sun's nursery. In that sense, every stellar nursery is both a place of new beginnings and an heir to the long history of stars that came before. The cycle of star birth and star death is the heartbeat of the galaxy. As we watch the new stars drift slowly from their birth cloud, we feel a gentle optimism. In the silent darkness, light has once again taken hold. These youthful suns will burn for ages, illuminating any worlds that gather around them and decorating the galaxy with their brilliance. One day, far in the future, they too will age, and their story will move into a new chapter. But for now, they rise from their birth nebula in radiant infancy, ready to live out their lives in the cosmic expanse. Leaving the dispersing nebula behind, we follow one shining young star out into the wider galaxy. The star glows steadily, a beacon of warm light amid the darkness. It has emerged from chaos and now settles into a long, stable existence. For millions, even billions of years, it will remain in this quiet middle age, faithfully converting its hydrogen fuel into light. The turbulent days of its birth are over. The calm radiance of maturity lies ahead. With the stellar nursery now fading in our cosmic rear view, we turn our attention to the star itself, to the long and luminous life that stretches before it. The journey of light that will span eons has begun. Now, freed from its turbulent birth cloud, our young star settles into a stable rhythm. Deep in its core, a raging furnace has ignited, yet on the outside the star appears tranquil and steady. Gravity pulls inward on the star's mass, while the immense heat and pressure from nuclear fusion push outward. These two forces find an exquisite balance. The star relaxes into a kind of cosmic adulthood, a long, calm middle age where it will shine consistently for eons. In this delicate equilibrium, the star's life truly begins in earnest, radiating energy into space in all directions. Our sun is one such star in this peaceful stage, quietly converting hydrogen into helium in its core. Every second, hundreds of millions of tons of hydrogen undergo fusion there. This process releases an immense flood of energy, but within the sun, it is a controlled, steady burn. The energy journeys from the core outward, bouncing among particles, gradually making its way to the surface over many thousands of years. By the time it departs the sun as sunlight, it has become the warm, life-giving glow we know. From our perspective on Earth, the sun's brightness is steady and comforting, rising and setting each day without fail. Yet that simple, gentle glow belies the titanic processes steadily humming within. Not all stars in this stable phase look alike, however. Stars come in a dazzling variety of sizes and colours, each with its own character. Some are truly colossal, 10, 20, even 100 times more massive than our sun. These giants blaze with a hot, blue-white light, pouring out energy at a prodigious rate. On a clear night, many of the brightest stars we see are of this kind. Massive stars burning their fuel furiously, illuminating their surroundings with intense brilliance. By contrast, the most common stars in the universe are far smaller and fainter than the sun. These are the red dwarfs, tiny crimson stars, often only a fraction of the sun's mass, some just a tenth or less. They glow with a subdued red-orange hue, so dim that not a single one is visible to the naked eye from Earth's skies, even though they swarm in our galaxy by the billions. Each star's color is a clue to its temperature and energy output. The blue-white giants are extremely hot, their surfaces tens of thousands of degrees, their cores hotter still. The Sun, with its familiar yellow-white light, has a surface about 5,500 degrees Celsius, around 10,000 degrees, moderate by stellar standards. The little red dwarfs are cooler, perhaps 3,000 degrees Celsius at the surface, glowing more softly. In the cosmos, color tells a story. Blue means fierce heat and youthful intensity. Red signifies a cooler, more modest output, often accompanied by remarkable longevity. Indeed, longevity varies drastically among stars. A massive blue star spends its fuel lavishly, shining so powerfully that it lives only a short time, maybe a few million years, before it exhausts its core fuel. In contrast, a small red dwarf sips its fuel slowly, conserving its hydrogen so well that it can shine on for hundreds of billions of years. In fact, the universe itself, about 13.8 billion years old, has not existed long enough for even the smallest red dwarf to run out of fuel. Not one of those tiny stars has died. They are all still out there, in their long, gradual burn, with lifespans that stretch far into the future. Our Sun lies in between these extremes. With a total life of around 10 billion years, it shines steadily for a very long time, but not forever. At roughly 4.6 billion years old now, the Sun is in comfortable middle age, having burned through about half of its hydrogen fuel. During these long ages, a star in its prime is a steady beacon. If we were to hover near such a star for generations, we would notice only subtle changes. The star might exhibit gentle pulsations or dark spots on its surface from magnetic cycles. Our Sun, for example, has an 11-year cycle in which its activity rises and falls. More sunspots and flares during the active phase, fewer during the quiet phase. But these are surface ripples on a vast, shining sphere. The Sun's overall brilliance and warmth remain essentially constant on human timescales, providing a reliable source of illumination and heat. This stability is crucial. It allows planets, if any orbit the star, to develop stable climates and for life to possibly take hold under a steady energy supply. On Earth, life has flourished for billions of years under the Sun's even glow, protected from its occasional outbursts by our planet's magnetic field and atmosphere. From the star's surface, energy streams out into the vast darkness of space. Each star pours light into the universe in all directions, a steady outflow traveling at the ultimate speed. Some of those photons will journey for years, centuries, or millennia before they ever encounter anything. Picture a single particle of light leaving the Sun. It races across the solar system, reaching Earth in just over 8 minutes. It will continue outward, perhaps eventually brushing past a distant planet or being absorbed by a grain of interstellar dust. Light from more remote stars can wander through space for decades or centuries, even millions of years, until maybe, just maybe, it reaches the eyes of a creature on some faraway world. In this way, each star broadcasts its presence across the galaxy, a lighthouse casting rays into the cosmic sea. Every twinkle we see in the night sky is a greeting from a distant sun, its light having travelled years across space to reach us. Among the multitude of stars scattered through our galaxy, we find solitary ones like our Sun, but also many that live in pairs or groups. In fact, a significant fraction of stars are members of binary or multiple systems, where two or more stars orbit each other in a gravitational dance. Some binary stars circle closely, perhaps exchanging gas or influencing each other's evolution with their gravity. From a distance, they might appear as one point of light, but up close, we would see two suns sweeping around a common center. There are binaries where one star's gravitational pull distorts or strips matter from the other if they are close enough, creating streams of gas or even periodic nova eruptions. Yet, during the stable midlife phase, many binary stars shine contentedly, each following its life cycle, tugging gently on its companion as they both orbit an unseen midpoint. We also find stars in larger families, open clusters that contain dozens or hundreds of stars born around the same time. Imagine being on a planet in such a cluster. The night sky would be a glittering canopy of bright stars, far more spectacular than the sky we see from Earth. Those stars are all siblings, moving together through the galaxy. Over millions of years, the cluster will gradually disperse as gravitational encounters and the tidal forces of the Milky Way pull the members apart. But while it lasts, it's a beautiful gathering of stellar kindred. Still, each star in the cluster lives out its own life, determined by its mass and internal processes, shining away the eons in parallel with its siblings. Inside the core of a main sequence star, as astronomers term this long, stable phase of hydrogen burning, the fusion of hydrogen steadily produces helium. Over time, the composition of the core slowly changes. Helium ash accumulates in the center as hydrogen is used up. The star very gradually adapts to these changes. In many cases, it grows slightly brighter over very long periods, as the core contracts and heats to compensate for the changing fuel mix. Our Sun, for example, is thought to be roughly 30% more luminous now than when it first settled into the main sequence billions of years ago. But such changes are extremely slow, imperceptible on any timescale shorter than millions of years. For millennia at a time, a star's appearance and energy output remain essentially constant. It's a testament to the self-regulating nature of stars. The outward pressure from the fusion fire balances precisely against gravity's inward pull, like a candle flame maintaining its shape against a gentle breeze. This phase of life, the radiant midlife of a star, can be thought of as the serene summer of a star's existence. The wild storms of infancy have calmed, and the trials of old age are yet to come. The star shines with mature grace, providing light and warmth to anything in its vicinity. If the star has planets, those worlds bask in its steady glow, perhaps developing atmospheres, oceans, and, on one lucky world, living creatures that thrive under its benign warmth. In our mind's eye, we can imagine distant solar systems with alien suns overhead, each star at peace in its prime, nurturing whatever planets circle it. Yet even in this stable idyll, time is inexorably marching on. Deep within the star's core, hydrogen is being converted into helium, and bit by bit, the available supply of hydrogen fuel is diminishing. For a star like the Sun, it will take billions more years for the core hydrogen to significantly deplete, an unimaginably long era from a human perspective. But for a more massive star, the clock ticks faster. A blue giant that might have started life with, say, 15 times the Sun's mass will burn through its core hydrogen in only 10 million years or so, a mere eye blink in cosmic terms. No matter the mass, eventually the day will come when the core can no longer sustain steady hydrogen fusion. The delicate balance that the star has maintained for so long will begin to shift. In a star's core, the first sign of trouble is when hydrogen runs low. The fusion reactions falter, reducing the outward pressure. Gravity, ever present, starts to squeeze the core tighter again. The core contracts, and as it does, it heats up, an outcome of energy conservation and increased pressure. In many stars, this contraction and heating ignites hydrogen in a shell around the core, where fresh hydrogen remains, which for a time provides a new source of energy. But this shell burning doesn't restore the old balance. Instead, it produces even more outward pressure on the star's outer layers. The result is dramatic. The star's outer regions begin to expand. The star, once stable and compact, grows in size, and its surface cools as it swells. The star's colour shifts toward red. Our steady yellow sun, for example, will inflate into a red giant when its time comes. Its diameter will increase enormously, by tens or even hundreds of times. By current calculations, in about 5 billion years, the sun's bloated form will likely engulf Mercury and Venus, and perhaps even reach Earth's orbit. If Earth survives that long, it would be scorched and then swallowed in the sun's fiery embrace. It is a dramatic fate, though one that lies in the far distant future, long after our planet has ceased to be habitable. All stars, regardless of mass, will face an end to their youthful stability. The signs of aging are often subtle at first, a slow increase in luminosity, a swelling of the outer layers, but eventually they become impossible to miss. The star's peaceful equilibrium is gone. What follows is the beginning of the end of the star's life, and it unfolds differently depending on the star's size. Stars, much like living creatures, cannot continue in their prime forever. After long ages of steady shining, a star eventually finds its fuel running low. The delicate balance that held it stable starts to waver. Now we follow our star as it leaves its long middle age and enters the twilight of its life. Imagine a star like the sun as it reaches old age. For billions of years, it quietly fused hydrogen in its core, but eventually that primary fuel is exhausted at the center. With less energy pushing outward from the core, gravity begins to gain the upper hand. The core of the star contracts under its own weight. As the core shrinks, it heats up dramatically, until a new kind of fusion ignites in a shell of hydrogen just outside the core. This change causes the star's outer layers to swell to enormous proportions. The star balloons into a red giant, a bloated version of itself with a much cooler surface that glows reddish-orange. In this swollen state, our sun will expand perhaps a couple hundred times its current diameter. Its atmosphere will billow outward into space. Once, it was a compact golden orb. As a red giant, it becomes a vast, puffy, reddish star. The sun's light will turn more ruddy and dimmer at the surface, though the total energy output actually rises due to its huge size. This red giant sun may engulf Mercury and Venus entirely. Earth's fate is less certain. It might be swallowed, or might just orbit uncomfortably close to the giant sun's roiling atmosphere. In either case, the Earth would be baked and barren by then. Thankfully, this transformation won't happen for roughly 5 billion years. As a red giant, the star is a very different entity. Its outer layers are enormously extended and tenuous, stretching out over space like a vast, luminous cloud. If we could see the sun at that stage, it would loom huge in the sky, and its once white light would be a deep amber hue. Meanwhile, in the star's core, big changes are underway. The core, now largely helium, the ash of the sun's long hydrogen-burning phase, continues to contract and heat as gravity presses inward. Eventually, the core gets hot enough, around 100 million degrees, to ignite helium fusion. Helium nuclei begin fusing into carbon and oxygen, releasing a new surge of energy. The star finds a brief new equilibrium. The core expands slightly, and the star's enormous red giant envelope might shrink and become somewhat hotter in color for a time. The star might move from a red giant to a somewhat yellower giant. For the Sun, this helium-burning phase will last only a fraction of the time of the preceding hydrogen-burning era, perhaps a few 100 million years at most. But this too is a finite phase. In a star of the Sun's mass, once the helium in the core is used up, no further fusion of heavier elements can ignite there. The core is now made of carbon and oxygen, products of helium fusion, and it will not reach the extreme temperatures needed to fuse those elements. Only more massive stars can. So the fusion fire in the core dies down for good. The star has one last desperate source of energy, a shell around the core where helium may fuse for a short while, and outside that, a hydrogen-fusing shell still burning. These multiple shells provide energy for a brief period, but they are unstable. The star begins to pulsate and convulse. It swells and shrinks in cycles, and with each pulsation it loses some of its mass. The once tightly bound outer layers now drift away, pushed by radiation and stirred by convection from the star's interior. In the final stages of a sun-like star's life, it gently sheds its outer layers into space. The dying giant star, over tens of thousands of years, puffs off its atmosphere layer by layer. What remains at the center is the hot core, small, dense, and exceedingly hot, while around it expands an enormous shell of gas. Initially, that gas may be too cool to glow on its own, but as the core is now exposed, it floods the surroundings with intense ultraviolet light. That high-energy radiation strikes the expanding shell of gas and causes it to fluoresce, like a neon sign. The result is breathtaking. A glowing, multi-layered bubble or ring of color, a planetary nebula, surrounding the tiny point of light that was once the star's heart. The term planetary nebula is something of a misnomer. It has nothing to do with planets. The name arose because, in early telescopes, these round, glowing clouds looked a bit like planetary disks. In reality, what we're seeing is a star's farewell performance. The dying star's cast-off layers form intricate shapes, sometimes a ring, sometimes a double-lobed hourglass, sometimes a complex filamentary structure. Every planetary nebula has its own unique pattern, sculpted by subtle differences in the star's final throes, or perhaps by unseen companion stars shaping the outflow. There are many famous examples. The Ring Nebula in the constellation. Lyra appears as a small smoke ring in the sky, a delicate oval of glowing gas about a light year across. At its center, through a telescope or in photographs, one can spot a faint blue-white star, the exposed core of the red giant, now a white dwarf, which is illuminating the ring. Another, the Helix Nebula in Aquarius, looks like a giant eye with a teal-blue iris and reddish outer rings, often dubbed the Eye of God in popular imagery. It too is a star's ghostly shroud, viewed nearly head-on. In Hubble Space Telescope images, these nebulae reveal astonishing detail. Clumps and knots of gas, symmetrical patterns perhaps shaped by stellar winds or magnetic fields, and multiple shells indicating pulses of mass loss. Each is a fleeting monument to the star that was. These nebulae will not last very long. The gas is expanding outward at tens of kilometers per second. In 10,000 years, 20,000 years, the shell will thin out and merge with the interstellar medium. The once bright nebula will fade from view, its atoms now simply part of the diffuse gas between stars. All that will remain of the star itself is the small central core. That core is now a white dwarf, an object about the size of Earth, but containing roughly half to a little more of the original star's mass. In the Sun's case, after it sheds its outer layers, about 50–60% of its mass might remain in the core. This Sun's remnant will be a hot white dwarf at around 100,000 K, nearly 18 times hotter than the Sun's current surface. White dwarfs shine from residual heat, not ongoing fusion. The nuclear fires are extinguished. What prevents the core from collapsing further is a quantum effect called electron degeneracy pressure. Essentially, the electrons in the densely packed matter resist being squeezed any closer, providing an outward pressure that balances gravity. A white dwarf is an incredibly dense state of matter. A teaspoon of white dwarf material might weigh tons, as the Sun's worth of mass is compressed into a sphere the size of a planet. Initially, the white dwarf is extremely hot and luminous, though tiny. Over time, it will cool. In the visible spectrum, it might be white-blue at first, then white, then yellow and red, and finally it will become a dark, cold object. But that cooling process takes billions upon billions of years. In fact, no white dwarf has yet cooled to truly dark, black dwarf status in the universe's 13.8 billion year history. As they cool, something fascinating happens inside. The carbon and oxygen in the core of the white dwarf can begin to crystallize, turning the heart of the star into a giant crystal lattice. In effect, the star is gradually solidifying into something akin to an enormous diamond of cosmic proportions. Astronomers have even observed evidence of this crystallization process in some nearby white dwarfs. One can poetically imagine a future, far distant, where the remnants of sun-like stars are dark, diamond-like spheres drifting through space, the final state of those stars after eons of cooling. And so, for a sun-like star, the final scene is one of quiet grandeur, a colourful nebula expanding and fading, and a tiny white dwarf left behind, glowing faintly like a coal, slowly cooling in the night. It is an end, yes, but not an absolute end. In dying, the star has returned much of its substance to space. The gas and dust expelled, rich in carbon, nitrogen, oxygen, and other heavier elements the star created during its life, will seed future cosmic clouds. These materials mix into the great galactic cauldron from which new stars will someday form. The cycle continues. In fact, the very elements that made life on Earth possible were forged in such stellar deaths. The calcium in our bones, the oxygen we breathe, the carbon in every cell of our bodies, the iron in our blood. Those atoms were once created in a star's interior and later scattered across space by a star's demise. We are literally made of star stuff, as the astronomer Carl Sagan once said. Without the death of stars, the universe would lack the rich palette of elements needed to form rocky planets or living organisms. Thus, a star's death, while marking the close of one existence, contributes to the genesis of new ones. It's a poignant, beautiful arrangement, creation and destruction entwined. Now consider a star far more massive than the Sun, perhaps 20 times the Sun's mass, or 50 times, or even more. Its life will end on a more violent note. After a relatively short but brilliant existence, maybe only a few million years, such a star also finds itself running out of core fuel. It too leaves the main sequence and swells up, becoming a red supergiant. If you want a visual reference, look at the star Betelgeuse, the bright red star marking the shoulder of Orion. Betelgeuse is a red supergiant nearing the end of its life, roughly 550 light-years away. It's a truly enormous star. If Betelgeuse were placed at the center of our solar system, its surface would extend well past the orbit of Mars and potentially approach or exceed the orbit of Jupiter. Betelgeuse's radius is on the order of 1,000 times that of the Sun. Such a star has a vastly distended, tenuous envelope and a relatively small core buried deep inside. It shines with tens of thousands of times the Sun's luminosity, but its surface is cool, hence the red color, around 3000 K. Deep inside, however, the core is extremely hot and busy. In these massive stars, when hydrogen in the core is exhausted, a complex sequence of events unfolds. The core contracts and heats, just as in smaller stars, but here the temperatures achieved are much higher. Soon, the core is hot enough to ignite helium fusion, if it hadn't already during a brief contraction phase. The star stabilizes for a bit, while helium burns to carbon and oxygen. But because the star is so massive, it does not stop there. When helium is depleted, the ever-crushing force of gravity contracts the core further, raising the temperature to the threshold needed to ignite carbon fusion. The star then fuses carbon into neon, magnesium, and other elements. This phase might last thousands of years, a blink compared to the star's initial main sequence life, which itself was only a few million years. When carbon runs out, the process repeats. The core, now largely neon and oxygen, contracts and heats again. Oxygen ignites, fusing into silicon and sulfur over a course of perhaps a few years. Then, in a final act, the silicon fuses into iron and nickel. But this last stage is astonishingly brief, on the order of days, or maybe weeks, for a very massive star. At this point, the star's interior resembles an onion-like structure, concentric shells, where different fusion processes occur. The outermost layers still burn hydrogen in a shell. Inside that, a shell of helium fusion, then carbon, then oxygen, then silicon, all surrounding an inert iron core at the very center. Each shell burns hotter and faster than the one outside it. The iron core grows quickly, but iron fusion is a dead end. Unlike the fusion of lighter elements, which releases energy, fusing iron absorbs energy. There is no additional source of pressure to be gained from fusing iron into heavier elements, which would be beyond iron on the periodic table. So once a significant iron core forms, maybe roughly 1.4 times the Sun's mass, the famous Chandrasekhar limit, the stage is set for catastrophe. This iron core is supported only by the pressure of degenerate electrons, similar to a white dwarf-like state, and by thermal pressure, but it is growing and becoming unstable. Finally, the core can no longer support its own weight. In a fraction of a second, the iron core collapses. Gravity crushes it at nearly a quarter of the speed of light. The conditions in the core reach mind-boggling extremes, densities rivaling an atomic nucleus, and temperatures on the order of billions of degrees. Protons and electrons are forced together, merging into neutrons and releasing floods of neutrinos, nearly massless particles that hardly interact with normal matter. The core, in essence, turns into a giant ball of neutrons, a nascent neutron star, in less time than it takes for your heart to beat. This collapse is halted abruptly when nuclear forces and neutron degeneracy pressure, the resistance of neutrons to further compression, come into play. The core, having shrunk to perhaps only 10 or 20 kilometers across, suddenly stiffens and rebounds slightly. The infalling outer core material slams into this hard surface and rebounds outward, driving a shockwave upward into the star. Meanwhile, the vast flood of neutrinos from the core's formation rushes out and imparts additional energy to the shock front. Within a second or two, the shock wave propagates through the star's interior, tearing it apart from the inside out. What happens next is one of the most spectacular events in nature: a supernova explosion. The outer layers of the star, which have been hurtling inward due to the core collapse, are violently ejected outwards by the shock. The star's core, now a neutron star, maybe the size of a city, remains at the center, or, if even that cannot support the mass, it collapses further into a black hole. But everything above that core is blasted into space. The energy released in a supernova is almost unfathomable. For a brief period, the dying star can outshine an entire galaxy of billions of stars. The energy emitted in those few seconds of core collapse and in the ensuing hours of explosion dwarfs what the star produced in its entire lifetime by many orders of magnitude, most of it carried away by neutrinos. From afar, a supernova appears as the sudden advent of a new star where none was visible before, or a previously faint star flaring to incredible brilliance. Humans through history have recorded a few such events in our own galaxy. One famous example, as mentioned, occurred in 1054 CE. Chinese and other astronomers noted a new star in the constellation we call Taurus. It was so bright that for a time it was visible in daylight. After about 2 years, it faded away from naked eye visibility. Today, at that location, we find the Crab Nebula, an expanding cloud of filaments about 6,500 light-years away, which is the remnant of that supernova. Inside the Crab Nebula lies a pulsar, a rapidly spinning neutron star that was the collapsed core of the star that exploded. It rotates about 30 times a second, flashing beams of radiation that make the nebula glow and pulse. How incredible to think that ancient sky watchers witnessed the death throes of a star, and nearly a millennium later, we can still see the gaseous remains and even the tiny spinning core that the star left behind. Another supernova was observed in 1604, Kepler's supernova, and before that in 1572, Tycho's supernova. Those were in our galaxy as well, though farther away and not as bright as the 1054 event. None have been seen in the Milky Way with the naked eye since Kepler's, which is a bit surprising because statistically a galaxy our size should have a supernova every century or so. It's possible some have occurred on the far side of the galaxy, obscured by dust, or perhaps we are just a tad unlucky in timing. However, with modern telescopes, we catch many supernovae in other galaxies every year, as tiny spots of light that appear and then fade over weeks, each the titanic death of a star in some distant galaxy. The aftermath of a supernova is twofold. First, there is the supernova remnant, the expanding shell of gas and dust from the exploded star. These remnants are often beautiful when viewed through telescopes, much like planetary nebula, but on a larger, more chaotic scale. The Veil Nebula in Cygnus is one such remnant, a wispy lace of glowing filaments filling a region of the sky several times the size of the full moon, all that remains of a star that blew itself apart perhaps 10,000 years ago. The colours in these remnants correspond to different elements. Oxygen might glow green or blue, hydrogen red, sulfur a deep red, etc. These are the elements the star forged in life and in death, now on display. Second, there is the compact object left at the centre. For many massive stars, that compact core becomes a neutron star. As we touched on, a neutron star packs more mass than the Sun into a sphere only about 10 to 20 kilometers across. It is essentially a giant atomic nucleus, a city-sized ball of neutrons. A teaspoon of neutron star material on Earth would weigh billions of tons. The neutron star is often born spinning very rapidly, since the parent star's rotation speeds up greatly as it collapses, like a spinning skater pulling in their arms. It also has an extremely strong magnetic field. These newborn neutron stars sometimes manifest as pulsars, cosmic lighthouses that beam radiation, which we will explore in a moment. However, if the original star was extremely massive, even the neutron star state cannot hold up. If the core remnant is above roughly 2.5 to 3 solar masses, gravity continues its inexorable crush, and the core collapses past the neutron star stage to become a black hole. In those cases, the star essentially vanishes from view, leaving a gravitational footprint and perhaps a brief burst of high-energy radiation, a gamma-ray burst, if conditions are right, as the only sign of its final collapse. Supernovae are extraordinarily important to the cosmic ecosystem. In the brief chaos of the explosion, many of the heavier elements in the periodic table are synthesized. Elements heavier than iron, such as gold, platinum, iodine, uranium, are created either in the supernova itself or in the neutron star mergers that sometimes follow. These elements are then flung into space, where they can become part of new stars, planets, and living organisms. Every piece of gold ever mined on Earth was forged in some stellar catastrophe long before the solar system existed, perhaps a supernova or the collision of two neutron stars. Moreover, the shockwave from a supernova can trigger the formation of new stars in nearby gas clouds. The explosion's blast compresses pockets of gas as it plows through space, and those pockets may collapse to form the next generation of stars. In that way, supernovae can sow the seeds for new stars, even as they herald the death of an old one. Thus, the death of massive stars, while violent, ensures that the universe is seeded with a rich array of elements, and that star formation continues. It's awe-inspiring to think that the iron in our blood, or the calcium in our teeth, was forged in the core of a star and spread across space by a supernova explosion. From a safe distance, a supernova remnant looks serene and lovely, a colourful nebula with perhaps a tiny pulsar blinking at its centre. But we know that each such remnant is the site of a cataclysm beyond comprehension. Still, in that destruction, there is renewal and revelation. Now, after the firestorm of a supernova, we are left with the core remnants, the neutron star or black hole. These objects are small, dark, or at least not shining by their own light in the usual sense, and would seem insignificant if not for their extreme properties. Yet, far from being idle, many neutron stars continue to play an interesting role in the story of the cosmos. They become beacons in the dark, signaling their presence across the light years. To these, we now turn our attention, the strange afterlives of stars, the pulsars and magnetars that blink and flicker in the cosmic night, and the silent, unseen pull of black holes that lurk in the shadows, in the silent darkness that follows a star's explosive death. A faint but steadfast rhythm can sometimes be detected across the cosmos. Imagine listening with a sensitive radio ear attuned to the stars. You might pick up a steady series of pulses, evenly spaced in time, like the precise ticking of an otherworldly clock. This is the signature of a pulsar, one of the most remarkable beacons in the cosmic night. A pulsar is a rapidly spinning neutron star that emits beams of electromagnetic radiation from its magnetic poles. As it rotates, these beams sweep through space. If one of those beams crosses Earth's line of sight, we detect a sharp pulse of radiation at regular intervals, the lighthouse effect on a cosmic scale. The discovery of pulsars in the late 1960s was a moment of both surprise and wonder. In 1967, a young astronomer named Jocelyn Bell, now Dame Jocelyn Bell Burnell, was poring over data from a new radio telescope when she noticed a peculiar signal. A string of pulses, each about a second and a third apart, extremely regular in their spacing. It was unlike anything expected from natural sources known at the time. For a short while, this mysterious signal was whimsically nicknamed LGM-1, standing for Little Green Men 1, because the regularity made some wonder, half in jest, if it could be a beacon from an intelligent civilization. However, as more observations were made, Bell found another, and then another, similar pulsing source in different parts of the sky, each with its own distinct period. Clearly, this was a natural phenomenon, not aliens, and one that was surprisingly common. The true explanation soon became evident. These were rapidly spinning neutron stars, exactly the kind of object predicted theoretically just a few years earlier by astronomers Franco Pacini and Thomas Gold. Jocelyn Bell had unwittingly discovered the first known pulsars. To picture how a pulsar works, imagine a neutron star, extremely dense, maybe 20 kilometers in diameter, spinning, say, once per second or faster. This neutron star has a very strong magnetic field, and around its magnetic poles, it accelerates charged particles and emits radiation, radio waves, light, X-rays, various energies. The magnetic poles are not aligned with the star's rotation axis, so as the star spins, the magnetic poles and the beams of radiation coming from them sweep around. If Earth happens to be in the path of those beams, we see a flash each time the beam points our way. It's exactly like a lighthouse lamp. The lamp's light is steady from within, but a distant observer sees it brighten and dim as the beam rotates past them. Thus, what we receive from a pulsar is a rapid series of flashes or pulses. The interval between pulses equals the star's rotation period. The precision of these pulses is astonishing. Pulsars can be more regular than the ticks of the finest clocks. Some pulsars rotate dozens of times per second. The fastest known spin about 700 times a second. These are called millisecond pulsars because their pulses repeat every few milliseconds. These millisecond pulsars are often old neutron stars that have been spun up by accreting matter from a companion star. They rotate so smoothly and predictably that their pulses arrive like clockwork. In fact, pulsar timings are so stable that astronomers have used them to test fundamental physics. One famous system is the Hulse-Taylor binary pulsar, two neutron stars orbiting each other, one of which is a pulsar. Careful timing of that pulsar's ticks revealed that the orbit was slowly shrinking, exactly as general relativity predicted, due to the emission of gravitational waves. This was the first indirect evidence for gravitational waves, and it earned the discoverers a Nobel Prize. More recently, networks of millisecond pulsars across the sky have been used as a giant detector for gravitational waves of very low frequency, potentially sensing the collective rumble of supermassive black holes merging in distant galaxies by tiny perturbations in pulse arrival times. Pulsars also serve as cosmic reference points. The idea of using them for navigation has even been tested. Their positions and periods are so fixed that one could theoretically triangulate a position in space by listening to pulsars. In a wonderful example of humanity sending out a cosmic roadmap, the plaques aboard the Pioneer spacecraft and the golden records on the Voyager probes include a diagram of the positions of 14 pulsars relative to the Sun, with the pulses' frequencies, or periods, encoded. The logic was that any intelligent beings finding the probe could use the unique periods of those pulsars, which would be known to them if they had mapped the galaxy, to identify our sun's location, and even the time that had elapsed since the spacecraft were launched, since pulsar periods gradually change in a known way. In essence, pulsars are like galactic lighthouses, each with its own characteristic flashing pattern, which we have used to mark our home address on a cosmic letter. Since Bell's first discovery, over 2,000 pulsars have been found. They are dotted throughout our galaxy, often in its spiral arms where massive stars lived and died. Many reside inside supernova remnants. For instance, the heart of the Crab Nebula contains the Crab pulsar, which spins about 30 times a second. Its pulses can even be detected optically with sensitive instruments. The neutron star is flashing on and off so rapidly that high-speed cameras can catch its flicker. The energy it releases powers the eerie glow of the Crab Nebula, causing it to pulse faintly in step with the pulsar. Another well-known pulsar is the Vela pulsar, from a supernova about 11,000 years ago, spinning about 11 times per second. Pulsars have a way of grabbing our imagination. These tiny objects, only a few miles across, spin with such speed and stability and produce such strong signals that one can hardly believe they are natural. But they are, and they represent physics pushed to an extreme. Over time, pulsars do slow down as they radiate energy. Their pulse intervals lengthen by tiny fractions. Occasionally, some pulsars undergo a sudden glitch, a slight speeding up. Astronomers believe this is due to a star quake or some internal adjustment in the neutron star's structure, making it spin a bit faster. Such glitches are another fascinating window into the exotic matter inside neutron stars. Not all neutron stars present themselves as regular pulsars. A particular subset, called magnetars, behave quite differently. Magnetars are neutron stars with magnetic fields about 1,000 times stronger than the typical pulsars, which is already huge. Instead of steady pulses, magnetars are known for sporadic, intense bursts of high-energy radiation. The magnetic field of a magnetar is so immensely strong, on the order of 10^-15 Gauss. By comparison, Earth's magnetic field is about 0.5 Gauss, that it can twist and stress the neutron star's crust. When the crust can't bear the stress, it slips, analogous to an earthquake, except it's a starquake. The result is a sudden release of energy and a burst of X-rays or gamma rays. One famous example occurred on December 27, 2004. Without warning, a magnetar called SGR 180620, located roughly 50,000 light-years away on the far side of our galaxy, emitted the most powerful flash of gamma rays ever recorded from beyond the solar system. In that split second, it released more energy than the sun emits in hundreds of thousands of years. The burst was so intense that it actually ionized Earth's upper atmosphere from across the galaxy. Fortunately, such magnetar flares are exceedingly rare, and this magnetar is very far away. But it shows that even in death, some stellar remnants can pack a punch. Most of the time, magnetars are relatively quiescent, maybe emitting faint X-rays as they spin. They rotate more slowly, perhaps once every few seconds. But their occasional tantrums remind us that neutron stars are not always the gently ticking clocks that pulsars can be. Some are more like sleeping dragons, prone to sudden outbursts. Between the steady beat of pulsars and the explosive hiccups of magnetars, neutron stars exhibit a remarkable diversity. They might appear as pulsating radio sources, or as steady X-ray sources, or as transient bursters. Some are in binary systems, accreting matter from a companion star and emitting X-ray pulses, X-ray pulsars, or bursts. If enough matter builds up and ignites in a thermonuclear flash on the surface, causing an X-ray burst. The cosmos has even provided systems where two neutron stars orbit one another. Sometimes both are pulsars, creating a clockwork of pulses that allow incredibly precise studies of gravitational physics. In recent years, another mystery has cropped up that could be related to neutron stars, or possibly other phenomena. Fast radio bursts, FRBs. These are extremely brief, millisecond flashes of radio waves, first discovered in 2007. They seem to originate from distant galaxies. Most FRBs are one-off bursts. They flash, and as far as we can tell, do not repeat. A few have been observed to repeat irregularly. Their origin is still not completely understood. Some theories suggest magnetars could be responsible. Perhaps during a flare or a starquake, a magnetar could emit a fast, focused burst of radio energy. In fact, one FRB detected in 2020 was traced to a known magnetar in our own galaxy, lending credence to that idea, though that FRB was weaker than the extragalactic ones. Other theories range from exotic, collapsing pulsars, strange quark stars, to speculative, signals from extraterrestrial technology, though most scientists think the explanation will be astrophysical. FRBs remain one of the hottest topics in astronomy because they are so enigmatic. They are like mysterious beacons that flash once and disappear, leaving us to puzzle over what kind of cosmic engine could be powering them. Listening to the universe in radio and gravitational waves, we have discovered that even in darkness there is sound and signal. Pulsars provide a rhythm, magnetars occasional crescendos, and perhaps FRBs are like sudden cymbal crashes in the great symphony of the cosmos. Through these, we learn about matter and energy under extreme conditions that can't be replicated on Earth. The study of pulsars has already given us tests of general relativity, a deeper understanding of neutron star interiors, and even a practical cosmic navigation tool. The study of magnetars is teaching us about the absolute limits of magnetic field strength and how quantum physics and plasma physics play out in those fields. For instance, magnetar fields are so strong they can polarize vacuum itself, an exotic QED effect. It is also poetic to consider what a pulsar sounds like if converted to audio. Some people have taken radio recordings of pulsars and sped them up into audible frequencies. The result is a steady beat, sometimes so rapid it becomes a tone. The Crab pulsar's 30 Hz pulse sounds like a deep hum or drone. A slower pulsar might sound like rhythmic ticking. These are the literal heartbeats of dead stars, the residual spinning heartbeat that continues long after the star's fiery heart has gone out. Amidst all these marvels, it's worth reflecting on the scale. A neutron star is tiny compared to the star it came from, but it packs an immense gravitational punch and dynamic behavior into that small package. They truly are like phantoms. The core of the star remains, but all the outer layers are gone. If you were nearby, a neutron star might just look like a little sphere, perhaps the size of a city, but you would feel its gravity well before you saw it. And if it's a pulsar, you might detect its pulse before you detect its physical form. It's as if these stellar remnants announce, "I am here," by these pulses of energy across space. As we drift away from a pulsar and its shimmering nebula, the regular blinks slowly recede until they are just a faint ticking in the distance. We have been fortunate to witness this strange second act of a star's life. But now, even those beacons begin to fade as we journey further into the dark. There is one final, ultimate state of collapse to consider, one where even the beacon is extinguished and nothing remains visible at all. pulsars and magnetars still communicate with the universe. There is light, or radio waves, X-rays, etc., emanating from them. But what about when a star's core collapses beyond the neutron star stage into a black hole? We then enter a realm where space and time themselves are warped into silence, and no messages can be sent out, at least not in light. To explore black holes, the dark hearts of the cosmos, we must leave behind the comfort of electromagnetic signals and venture into a region defined by pure gravity and mystery. From the steady cadence of pulsars, we now turn to the soundless void of the black hole, the final and most enigmatic chapter in the life cycle of massive stars. Beyond the glowing remnants and the flashing pulsars, we approach something truly ominous and mysterious. A place of absolute darkness and inexorable gravity. Here lies the black hole, the end state of complete collapse. A black hole is, in essence, a region of space-time where gravity has become so strong that nothing can escape from within, not even light. It forms when a mass is compressed into a volume so small that the escape velocity from its surface exceeds the speed of light. In the case of a star, this happens when a very massive core collapses beyond the neutron star stage. All the star's mass falls into an infinitely dense point, a singularity, according to classical theory, and an event horizon forms around it. The event horizon is the boundary of no return. Anything that crosses this invisible sphere around the singularity is lost to the outside universe forever. It can never climb back out, because doing so would require moving faster than light. Approaching a black hole is like approaching a bottomless pit in space-time. From a distance, you might not notice anything unusual except that the gravity is getting stronger. But as you get closer, you'd see strange optical effects. Light from background stars would bend around the black hole, distorting the star field into rings or arcs, gravitational lensing. You might even see multiple images of the same star, or a ring of light called the photon ring, which is composed of light rays that are almost trapped in orbit around the black hole. The black hole itself would appear as a circular patch of blackness, silhouetted against whatever lies behind it, because it emits no light, and any light passing too close falls in and vanishes. If you were to fall toward a stellar mass black hole, the tidal forces, the difference in gravity's pull between your feet and head, would grow enormous. Well before you reach the event horizon, you would likely be pulled apart, a process grimly nicknamed spaghettification, as you would be stretched into a long, thin shape. For a supermassive black hole, interestingly, the tidal forces at the horizon could be relatively mild due to the black hole's huge size. You might actually pass through the event horizon of a supermassive black hole without immediate harm. You wouldn't even necessarily notice the exact moment you pass the horizon, since nothing physical marks it. But once inside, gravity would intensify, and eventually any object would be torn and crushed as it approaches the singularity at the center. What does time feel like near a black hole? This is one of the strangest aspects. To a distant observer, time near the black hole appears to slow down. If you watched a spacecraft falling into a black hole, you'd see its clocks tick more slowly, and its movements become sluggish as it neared the horizon. Light from the craft would also get more and more redshifted, stretched to longer wavelengths, eventually beyond red into infrared, microwave, etc., and dimmer. In fact, from our perspective, the craft would never be seen to quite cross the horizon. It would approach and fade, asymptotically freezing right at the edge, its image growing redder and fainter until it vanished. But the craft itself, in its own frame of reference, would experience time normally. it would cross the horizon in finite time and head toward the center. This discrepancy is due to gravitational time dilation. Time runs slower in stronger gravity, as seen from outside. So in a way, the act of collapse that forms a black hole, or anything falling in, appears paused at the horizon to external eyes, though that is an illusion caused by the extreme warping of space-time. For many years, black holes were purely theoretical constructs predicted by Einstein's general relativity. But over the past few decades, evidence for them has mounted and become unassailable. In the 1960s and 70s, strong X-ray sources like Cygnus X1 provided the first clues. Here was an invisible object of 10-pound solar masses pulling matter off a companion star, too massive to be a neutron star, which max out at 3 solar masses or so. So a black hole was the likely culprit. As mentioned, in the centers of galaxies, the motions of stars, like those orbiting Sagittarius A, pointed to a huge mass in a tiny space. Again, the only plausible explanation was a supermassive black hole. Then came the revolutionary image in 2019, humanity's first glimpse of the immediate vicinity of a black hole. The Event Horizon Telescope team linked radio dishes around the globe to act as one giant telescope and peered at the nucleus of the galaxy M87, 55 million light-years away. The image they reconstructed showed a bright, thick ring of light with a dark center, exactly what theory predicted for a glowing disk of gas around a black hole, with the black hole's shadow visible. The dark region in the center is roughly the size of our solar system, which for a black hole of 6.5 billion solar masses corresponds to the diameter of its event horizon, about 40 billion kilometers across. It was breathtaking to see the predictions of relativity so vividly confirmed. The image even showed a slight asymmetry in brightness in the ring, attributable to relativistic beaming. Gas on the side of the ring spinning toward us appears brighter than gas on the receding side. In 2022, the same technique yielded an image of our own Milky Way's central black hole, Sagittarius A. That one was trickier. Sag-A is much smaller, and the gas moves faster, blurring the image. But it too showed a ring of emission with a dark center, consistent with a 4 million solar mass black hole. Beyond images, we have heard black holes via gravitational waves, as mentioned earlier. When black holes merge, they emit a burst of gravitational radiation. LIGO and its partner Virgo have by now detected dozens of such mergers. The data from these events provide estimates of the black hole's masses and spins, and even allow tests of general relativity in the strong field regime. So far, Einstein's theory has passed all tests. The waves' shapes match the predictions very well. We've detected black holes of various sizes merging, from about 5 solar masses up to a record 85, and 66 solar mass black holes merging into one of about 142 solar masses, the first evidence of an intermediate mass black hole in the 100s of solar masses range. Each detection is like hearing a faint chirp in the darkness, the final call of 2 black holes as they become one. Black holes have also become central characters in our quest to understand the universe's large-scale behavior. The growth and activity of supermassive black holes in galaxies are thought to influence galaxy evolution profoundly. In young galaxies, when gas is plentiful, the central black hole can devour matter and shine as a quasar. The energy output can be so tremendous that it blows out or heats surrounding gas, potentially suppressing star formation. This feedback loop might explain why galaxies have the sizes and star counts they do, and why there seems to be a correlation between the mass of the central black hole and properties of the host galaxy's bulge. It's as if the galaxy and its black hole co-evolve, regulating each other. There's a deep and fascinating mystery about the very existence of supermassive black holes in the early universe. We see quasars, powered by black holes of 1 billion solar masses, at epochs when the universe was less than 1 billion years old. How did black holes grow so big so fast? It challenges our understanding of black hole formation and growth, suggesting that either some black holes started off with a head start, perhaps through direct collapse of massive primordial gas clouds, or they grew through constant, efficient accretion and mergers. It's an area of active research. Now, no discussion of black holes is complete without mentioning Hawking radiation again and what it implies. Hawking's theory united thermodynamics, quantum mechanics, and relativity in a beautiful way by assigning black holes a temperature and entropy. The entropy of a black hole is proportional to the area of its event horizon. In fact, one of the largest entropy objects in the universe. The idea that black holes can evaporate leads to one of the most profound puzzles in physics today, the information paradox. When a black hole evaporates, what happens to the quantum information of the stuff that fell in? Does it come out scrambled in the Hawking radiation? Does it remain lost behind until the end, somehow preserved? Or is our understanding of quantum mechanics or space-time incomplete, such that the paradox is resolved in a deeper theory? Many believe the resolution lies in quantum gravity, perhaps string theory or loop quantum gravity, or some idea not yet conceived. This paradox has led to concepts like firewalls or holographic principles, the idea from string theory that all the info in a volume can be encoded on the boundary surface, famously realized in the ADS-CFT correspondence. It's mind-bending stuff, all triggered by considering black holes carefully. As we float now, at what we imagine is a safe distance from a black hole, perhaps at the edge of a glowing accretion disk, we might witness a jet of plasma shooting out from near the black hole's pole, powered by the twisting magnetic fields and the black hole's spin. We look at the yawning black sphere where light disappears. It is forbidding, yet we know that black holes are common outcomes of nature. Our own galaxy likely has millions of stellar mass black holes scattered about, undetectable unless they interact with something. One might be relatively nearby. The closest known is a few thousand light years away. But space is immense, and these black holes are needles in a haystack. Unless they accrete or lens background stars, we'd never notice them. At this point, we have traced the journey of matter from diffuse gas to star's demise, through white dwarfs, neutron stars, pulsars, and black holes. We have seen how the cosmos recycles material, and how even in death, stars contribute to the cosmos's continuing story. It's a grand, interconnected narrative, spanning billions of years and trillions of kilometers. Yet, the story is not over. In fact, in many ways, we've only been looking at individual threads. Now it's time to step back and admire the entire cosmic tapestry. The stars themselves are just points of light sprinkled across galaxies. Galaxies form clusters and filaments on the grandest scales. And underlying all of this are deeper mysteries. Unseen dark matter holding galaxies together. A puzzling dark energy accelerating the expansion of the universe. The echoes of the Big Bang still detectable as a faint microwave glow in every direction. And the ultimate question of how the cosmos began and how it might end. We also have scarcely touched on the question of life. The possibility that amid all those countless stars, we are not alone. That there are other eyes observing the cosmos from planets we will never perhaps see. Our journey through the cosmos will continue as we leave the vicinity of this black hole, letting its darkness recede behind us. we turn our gaze to the vast expanse beyond. In the soft starlight of billions of galaxies, we will search for understanding of the universe's larger structure and origin. From the tiny, intense realm of collapsed stars, we now lift our perspective to the widest vistas, the swirling galaxies, the web of matter that binds them, the cosmic horizon itself. The night is far from over. It is opening out into an even greater panorama of wonder. And as we prepare to venture forth, we carry with us the knowledge gained from our sojourn among the stars, that we are part of an ever-evolving, ever-resplendent universe, one that invites us to explore further and deeper in part 3 of our journey through the cosmos. The cosmic ocean stretches out before us, and many more wonders await just over the horizon. Let us continue onward, gently into that vastness, with curiosity and awe as our guides. As we drift beyond the edges of our familiar cosmic neighborhood, a subtle pattern begins to emerge in the darkness. Our journey carries us far outside our home galaxy, beyond clusters of galaxies, and into the grand expanse of the universe. In the silent void between island universes, something remarkable becomes clear. The galaxies are not scattered randomly. They are arranged in a vast and delicate structure, an immense pattern stretching across the cosmos like an ethereal web. Each galaxy glitters as a tiny island of light, but seen from afar, together they trace the filaments of this cosmic web. Imagine rising high above the universe, looking down at this immense tapestry. Countless galaxies linked by faintly glowing threads of gas and invisible matter, forming luminous filaments that span hundreds of millions of light years. Between these filaments lie enormous voids, realms of almost unimaginable emptiness, where scarcely a galaxy can be found. On the grandest scales, the universe resembles a spider's web, or even the neurons of a giant brain, a network of filaments and nodes connected across unfathomable distances. This is the cosmic web, the largest structure we know of in existence. Within its strands, galaxies cluster like dewdrops clinging to a cosmic spider's silk. In the densest knots of the web, hundreds or even thousands of galaxies crowd together, forming colossal clusters. Our own Milky Way is part of this vast design, belonging to a small cluster of galaxies bound together by gravity. That cluster itself is nestled along an outlying strand of an immense supercluster. Everywhere we look on these scales, we see the same pattern, an endless lacework of matter and light. In these crowded cosmic cities, galaxies interact and sometimes collide. When galaxies drift too close, gravity draws them into a slow dance that can last millions of years. Two galaxies may swirl around each other, merging into one larger galaxy in a grand cosmic embrace. Such mergers can trigger the birth of new stars as gas clouds compress, briefly lighting up the darkness with starburst brilliance. Our own Milky Way is part of this vast design, belonging to a small cluster of galaxies bound together by gravity. That cluster itself is nestled along an outlying strand of an immense supercluster. Everywhere we look on these scales, we see the same pattern, an endless lacework of matter and light. Astronomers have given our home supercluster a beautiful name, Laniakea, meaning immense heaven. It encompasses our galactic neighborhood and countless other galaxies in a single flowing structure. The name feels fitting, for we truly find ourselves in an immense heaven of galaxies. Yet even Laniakea is just a tiny patch of the cosmic web. The filaments of this web stretch far beyond, connecting our supercluster to others in all directions, spanning the observable universe. To put it in perspective, everything we know, our entire Milky Way, with its hundreds of billions of stars, is just a single gleaming point along one filament of the web, a mere drop in an ocean of galaxies. It is a humbling vision. Trillions of galaxies are woven into this cosmic lattice, each galaxy a gleaming node in the darkness. And yet, most of the cosmic web is actually invisible to us. Only a small fraction of matter shines as stars. The rest, vast clouds of thin gas and an even greater amount of mysterious dark matter, traces out the filaments without ever showing itself directly. This dark matter is like an unseen scaffold, its gravity gently drawing galaxies and gas into these cosmic highways. Along these unseen highways, rivers of primordial gas stream toward the galaxies. Funneled by gravity, this gas feeds galaxy clusters, providing fuel for the birth of new stars. In a sense, the cosmic web is like a cosmic bloodstream, circulating matter and energy and sustaining the galaxies that shine within it. Threaded through the gaps is something even more enigmatic. Dark energy, a subtle pressure woven into the fabric of space, pushing the universe outward and stretching the web ever wider over billions of years. How did such a structure come to be? In the aftermath of the Big Bang, matter was almost uniformly spread out, like a mist filling space, but not perfectly uniform. Tiny ripples and whispers of higher density were scattered about. Over time, gravity began to amplify those slight irregularities, drawing matter ever so slightly more into the dense spots. Slowly, the first threads of the cosmic web emerged as matter drew together along invisible lines. Over billions of years, those threads pulled in more and more material, growing thicker and more pronounced. Where several filaments crossed, galaxies amassed into clusters and superclusters, great nodes in the web. Meanwhile, the vast spaces in between, cosmic voids, grew emptier as matter flowed out of them into the filaments. From a nearly smooth beginning, a delicate pattern blossomed into the immense cosmic web we see today. In fact, a faint afterglow of the Big Bang itself, the cosmic microwave background radiation that bathes the universe, contains a subtle imprint of those first seeds of the cosmic web. We see it as a nearly uniform glow of microwave light from every direction, but with tiny variations in temperature. Those slight ripples are the very ones that grew into the vast structure we know today. It's awe-inspiring to realize that the grand design of the cosmic web was encoded in the cosmos's baby picture billions of years ago. Surveying the skies, astronomers painstakingly charted the positions of millions of galaxies, revealing the cosmic web's pattern on their maps, filaments and clusters clearly emerging from the data. It was like turning on a cosmic lamp to illuminate a dark room. Suddenly, the outlines of the web appeared, where before we saw only isolated points of light. Curiously, the pattern of the cosmic web, galaxies linked along filaments, evokes structures we see elsewhere in nature. It brings to mind the filigree of spiderwebs, the branching veins in a leaf, even the neural pathways in a brain. At vastly different scales, similar designs emerge, echoing a universal theme of connectivity. It is a reminder that the universe, from the microscopic to the cosmic, favors certain elegant patterns. And it hints that we, with our intricate networks of neurons, are in some way a reflection of the cosmos that produced us. There is also a profound perspective that comes from seeing the universe in this way. Our Milky Way, with its spiral arms and its hundreds of billions of stars, seems enormous on a human scale, yet it is but a single thread in this almost immeasurable tapestry. When we contemplate the cosmic web, we are reminded of how small our home is and how interconnected everything can be. We are made of atoms, forged in stars that reside in a galaxy, which in turn is a node in this web of matter spanning the cosmos. In a sense, we are part of that web, the same cosmic story that shaped galaxies also shaped us. Yet even this colossal web that we can observe may be only a fragment of a greater whole. The observable universe stretches about 46 billion light-years in all directions from our vantage point, an immense sphere of space-time containing everything we have ever seen. Beyond that horizon, there may be more cosmic web, more galaxies, perhaps endlessly repeating into the unknown, or perhaps something altogether beyond our understanding. We do not know, for any light from beyond that cosmic horizon has not had time to reach us, and perhaps never will. From our tiny corner of the cosmos, we gaze out as far as we can, to the edge of what is observable. At that far frontier, the cosmic web simply fades into darkness, the last faint galaxies disappearing at the limits of the knowable cosmos. Standing at that dim frontier, we are faced with mysteries that beckon us onward. This realization stirs profound questions within us. What lies beyond the farthest reaches of the cosmic web? Is there an edge to space, or does the tapestry of galaxies continue forever into the endless night? And what of time? Did time have a beginning, and will it have an end, or is it as boundless as the space it accompanies? Such questions beckon us to step beyond the comfort of what we know. They invite us to explore realms that transcend our familiar dimensions, to journey into the unknown, where our ordinary ideas of distance and duration may no longer apply. We now venture beyond the limits of the known, into realms where the very fabric of reality is stretched to its extremes. The cosmic web revealed the grand structure of our universe, but it also brought us to the edge of what we can see and comprehend. To go further, we must step beyond the boundaries of space and time as we know them. This is a journey into the abstract and the mysterious, where intuition falters and wonder takes the lead. Space and time, the two fundamental dimensions of our experience, are deeply intertwined. We often think of them as separate. Space as the endless expanse we move through, and time as the flow of moments we move in. Yet modern physics has shown that they are woven together, forming a four-dimensional fabric called space-time. Massive objects like stars and planets bend this fabric, causing what we perceive as gravity. In a sense, gravity is not so much a force pulling objects together, but the result of objects following the curves in space-time created by mass. This means that space can stretch and curve, and time can slow down or speed up, depending on the circumstances. Consider time itself. It is not absolute. If you were to travel through space at speeds close to the speed of light, time for you would slow relative to those you left behind. A year might pass for you, while decades pass elsewhere. Imagine an astronaut embarking on a near light-speed journey among the stars. To the astronaut, the trip might seem to last only a few years, but when they return home, they could find that many generations have come and gone on Earth. In a very real way, that traveller would have leapt into the future. This isn't science fiction. It's a consequence of Einstein's theory of relativity, verified by experiments. We see tiny examples of it in our technology. The satellites that provide GPS signals have to account for time running slightly differently in orbit than it does on the ground, due to their high speed and weaker gravity. Gravity, too, affects the flow of time. The stronger the gravity, the slower time moves. Again, from the perspective of an outside observer. If you were to hover near the surface of a neutron star, or at the edge of a black hole, time for you would pass significantly slower than for someone far away. To distant eyes, you would appear almost frozen, your movements and clocks crawling along. Even here on Earth, the effect exists on a tiny scale. Time runs just a little bit slower on the planet's surface than it does high above in space. The difference is minuscule, but measurable with precise instruments. It's as if time is a rubber band that can be stretched by speed and gravity. What happens then when we push these ideas to their extremes? Take the enigmatic case of black holes. A black hole forms when matter collapses so densely that space and time themselves warp into a kind of cosmic trap. The boundary of a black hole is called the event horizon, a point of no return. Cross that boundary, and even light cannot escape the black hole's gravitational pull. From the outside, an object falling toward a black hole appears to slow down and never quite falls in. Time, from our view, nearly stops at the horizon. From the falling object's own perspective, time continues normally, but they drift into a realm we cannot observe or communicate with. Inside a black hole, our understanding of physics breaks down. Space and time themselves might exchange roles or come to an end at the central singularity, a point of infinite density. It is a place where the familiar meaning of beyond truly applies, beyond our ability to see, beyond our current understanding of space and time. The idea of going beyond space and time also leads us to the concept of higher dimensions and alternate realities. We humans perceive 3 dimensions of space: length, width, height, and one of time. But what if there are more dimensions beyond these? Some scientific theories, like string theory, suggest that additional spatial dimensions could exist, curled up so small that we don't notice them. It's hard to visualize extra dimensions, but analogies can help. Imagine 2-dimensional beings living on a flat sheet of paper. They know only forward, backward, and left, right. The concept of up or down off their page is completely foreign. Now, as 3-dimensional beings, we can lift that paper and move those flat creatures out of their plane, an action that, to them, would seem impossible or magical, like disappearing from one location and reappearing in another without crossing the space in between. In a similar way, if a 4th spatial dimension exists, it might allow shortcuts through our 3-dimensional universe that are invisible to us. We call such hypothetical shortcuts wormholes, tunnels through the higher dimensions connecting distant points in our space and time. Wormholes have been popular in science fiction and theoretical physics alike. In principle, if space-time can be curved by gravity, it might be curved enough to fold back on itself, allowing one region to connect to another, like 2 pages of a book touching. A wormhole would be like a bridge or tunnel, linking 2 far-apart locations in the universe, or perhaps 2 different times, or even 2 different universes entirely. So far, wormholes remain speculative. We have no evidence they truly exist. They appear possible in equations, but nature has yet to show us one. If they do exist, they might be unstable or extremely short-lived, pinching off before anything could travel through. Yet the idea is tantalizing, a literal shortcut through space and time, a way to step outside the normal flow and emerge somewhere, or somewhen, else entirely. Beyond even wormholes lies the idea of a multiverse, the notion that our universe might be one of many. When we gaze out at the cosmic web, we are seeing only the contents of our own universe, limited by the speed of light and the beginning of time as we know it. But some theories propose that what we call the universe is just one bubble in an infinitely larger cosmic ocean. Our Big Bang may have been just one of countless Big Bangs sprouting other universes, each with their own space, time, and perhaps different laws of physics. This grand multiverse is a highly speculative idea, but it arises naturally in some interpretations of cosmic inflation, the super rapid expansion that happened in the first fraction of a second after our Big Bang. If space can stretch indefinitely, it might create separate realms that disconnect from each other, each becoming a universe in its own right. Those other universes could be floating in higher dimensions beyond our reach, like islands in a sea we cannot cross, forever unreachable and unseen, but possibly real. Thinking about such possibilities can be dizzying. We find ourselves asking, where does it all end? If there's a multiverse, is there something beyond that? Perhaps an endless hierarchy of realities? Human imagination can run wild, but at some point, we must admit, we simply do not know what lies beyond the boundaries of our observable reality. These concepts, extra dimensions, wormholes, multiverses, highlight how much more might exist beyond the slice of reality we experience. They remind us that space and time might be much more expansive and strange than our everyday senses tell us. Even the concept of time's beginning and end is a deep mystery. According to our best understanding, time as we know it began with the Big Bang, roughly 13.8 billion years ago. It's often said that asking what came before the Big Bang may be meaningless, because time itself might have started then, much like asking what's north of the North Pole. Yet scientists have proposed daring ideas that peek beyond that initial moment. Some suggest our Big Bang could have been the result of a previous universe ending, a kind of cosmic rebirth in an eternal cycle of universes expanding and contracting. Others imagine collisions between brain worlds, objects in higher dimensions, sparking new universes. These ideas remain speculative, but they serve to remind us that the origin of space and time is still an open question. The far future of time is another boundary to ponder. Will time extend eternally forward, or is there an end? If the universe keeps expanding under the influence of dark energy, trillions of years from now, the galaxies beyond our local group will drift out of view, and the stars will gradually fade out. The arrow of time, which we experience through growth, aging, decay, points toward an ever colder, more diffuse cosmos in the distant future. But some have wondered if time could somehow loop back on itself, or if new Big Bangs might ignite after the death of our universe, renewing the cycle. These ideas are speculative poetry, musings at the edge of what science can say. While these grand questions remain unanswered, we have at least learned how flexible the fabric of reality can be. Space can bend and expand. Time can slow, and perhaps, under extreme circumstances, even stop from one point of view. And beyond the farthest stars we see, there may lie realms entirely outside our comprehension. Amidst these abstractions, it is comforting to remember that even if we cannot step outside space and time, we can still explore amazing wonders within them, having stretched our thoughts to the cosmic horizon and beyond. We gently return our focus to the universe we inhabit. Within our own space and time, within this vast cosmos we call home, there are countless worlds and marvels yet to discover. We turn now to one of the most inspiring revelations of the modern age, the existence of worlds beyond number, orbiting stars across the galaxy and beyond. The night sky has forever been filled with stars, but only recently did we learn that most of those stars are accompanied by their own families of planets. In the past, we could only wonder if other worlds existed beyond our solar system. Now we know that they do. in astonishing abundance. We have found thousands of planets orbiting distant suns, and we suspect there are billions upon billions more, far too many to ever count. It turns out that planets are as common as the stars themselves. Indeed, there may be more worlds than stars in the Milky Way. We live in a galaxy awash with planets, truly worlds beyond number. These distant planets are called exoplanets, and they come in an incredible variety of sizes, compositions, and environments. Some are giant balls of gas, even larger than Jupiter, orbiting so close to their stars that their atmospheres are heated to thousands of degrees. On these hot Jupiters, a year can last only a few days, and clouds of strange materials might rain drops of molten glass or metal. Imagine a place where the daytime sky glows a yellow-white from the fierce heat of a nearby sun, and gusting winds carry shimmering grains of glass sideways through the searing air. Such alien weather is likely commonplace on some of these distant giants. Other exoplanets are small, rocky spheres, like Earth. We've discovered worlds a bit larger than our own, called super-Earths, and others slightly smaller than Earth. Some bake under intense starlight, while others are shrouded in eternal twilight. One planet might be a scorched ember, with a sun so close that its surface is an endless ocean of lava. Another might be a cold, dimly lit rock, where the faint glow of a red dwarf star casts perpetual dusk and sheets of ice cover the ground. Yet another could be a water world, a planet covered entirely by a deep global ocean without any land at all, its surface a ceaseless rolling sea under an eternal blanket of clouds. The diversity of worlds is beyond anything astronomers imagined when they first began searching. We've found planets with 2 or even 3 suns in their sky, circling multiple star systems in complex orbits. Around some stars, planets orbit so tightly packed that their neighbouring worlds loom large, visible as bright points or even disks in each other's skies. Around others, we find solitary planets in wide, slow orbits, taking centuries to circle their sun. No 2 solar systems are quite alike. Each is its own cosmic garden with a unique layout. Even our own solar system, with its 8 planets and myriad moons, is just one example of a planetary system, and not an especially extreme one. In our system, the planets orbit in mostly circular paths, all in a single plane, and our Sun is a fairly ordinary star. Elsewhere, we've detected systems where planets swing in elongated paths or tilt at wild angles, or where massive planets hug their stars at distances far closer than Mercury is to our Sun. The universe seems to delight in variety. There are gas giants so near their stars that they are puffed up by stellar heat, their atmospheres slowly bleeding away into space. There are planets that orbit pulsars, the leftover cinders of supernova explosions, meaning those worlds survived the violent death of their star and now receive only the eerie flicker of radio waves from the spinning pulsar. One of the most striking discoveries has been planets that might resemble our Earth in key ways. Among the thousands of exoplanets, a precious handful have been found in what's called the habitable zone around their stars. Not too hot and not too cold, where liquid water could potentially exist on the surface. Some of these planets are rocky and similar in size to Earth. We cannot yet say if they have oceans or atmospheres like ours, but simply knowing they exist raises exciting possibilities. For instance, a small and faint star not far from us was found to harbour 7 Earth-sized planets in a tight embrace. A few of those worlds lie in the temperate zone where sunsets might sparkle off alien seas, if those planets indeed have water. And around the very closest star to our Sun, astronomers detected a planet slightly larger than Earth that sits in that star's habitable zone. Though that nearby world remains mysterious, it underscores that potentially life-friendly planets could be practically next door in cosmic terms. How do we find these distant worlds, given that they are so tiny and faint compared to the stars they orbit? Astronomers have become exceedingly clever at listening to the subtle whispers of planets. They watch stars for the slightest dip in brightness that happens when a planet passes in front of its star. A transit, like a moth briefly flying across a searchlight. When such a minuscule eclipse occurs, the star's light dims by a tiny fraction. And from this we infer the presence of a planet, estimate its size, and even glean hints about its atmosphere. Other times, scientists measure the gentle wobble of a star caused by the gravitational tug of orbiting planets. By detecting these wobbles, they can tell that a planet is there and gauge its mass and how far it orbits from the star. Through these patient methods, watching winks of starlight and listening for stellar wobbles, humanity has mapped a vast menagerie of new worlds without ever leaving our own. On a few rare occasions, we have even managed to capture direct images of exoplanets. This is an astonishing feat, like trying to spot a firefly next to a floodlight from thousands of miles away. By using advanced techniques to block out the star's blinding glare, telescopes have photographed several young giant planets. In those images, the planets appear as tiny dots of light near a brilliant star. But those dots are indeed distant worlds, glowing faintly with the heat of their formation. These direct snapshots allow us a first glimpse at alien sunsets and unknown landscapes, even if only as specks of light. It's a bit like seeing a candle flame flicker in front of a lighthouse, faint and small, but enough to stir the imagination. What we are finding is that planets are ubiquitous. Every time we develop a new instrument or method to look for them, we discover more, smaller ones, farther ones, stranger ones. It seems that wherever nature can put a planet, it does. And not only planets, moons too may abound. In our own solar system, some moons are geologically active or harbour subsurface oceans. It stands to reason that exomoons, moons around exoplanets, could also be diverse and potentially hospitable. We have yet to definitively find an exomoon, but searches are underway, and there are tantalizing hints in the data that one might have been spotted. When we pause to reflect on the scale of it all, the reality of these myriad worlds can be profoundly moving. Every twinkling star in the sky is not just a point of light, but likely a whole system of planets, a collection of other skies and other horizons. Some of those worlds might be barren rock or gas, but some could be rich with clouds, rivers, and perhaps even life. It's humbling and exhilarating to realize that the cosmos has been creating planets for billions of years, scattering them throughout the galaxy like seeds on the wind. Picture standing on one of those distant shores. Perhaps it's dusk on a world orbiting a red dwarf star. The sky is dimly lit in deep crimson, and two pale moons hang above an alien ocean. Gentle waves lap against a foreign shoreline under constellations entirely different from those we know. Or imagine a massive planet made mostly of ice, orbiting far from its star. Its sky might be almost black at noon, with the faint sun just a bright star in the distance, and rings of frozen debris arcing overhead like a pale ribbon. The possibilities are endless and enchanting. As we catalogue more of these distant worlds, we inevitably wonder about their stories. How do planets form in such variety? Are there places where life has started, as it did on Earth? the stage is set for the next profound step, to learn which of these myriad worlds might harbour living things or even intelligent observers. The sheer number of planets gives us hope that we are not alone, yet so far we have heard only silence from the great cosmic ocean. Still, the discovery of these worlds has made the universe feel more intimate in a strange way. No longer are we confined to the handful of planets around our sun. We are members of a vast community of worlds. The existence of these worlds beyond number invites us to think differently about our own planet as well. From a distant vantage, Earth itself is just another exoplanet orbiting an unremarkable star. What would alien scientists see if they observed our sun from light years away? They might notice a slight dimming every year as our planet transits, and a gentle wobble in the star's motion, clues that a small, temperate world orbits here. It's a reminder that our planet, with all its life, history, and humanity, is one of many. Just as we wonder about those other worlds, perhaps someone out there might be studying ours. Gazing up on a clear night, when you see the glitter of countless stars, you can now know that hidden in that sparkle are untold new worlds. Some of those worlds will be utterly alien, with environments we can scarcely imagine. Some may be kindred to Earth, with water and rock and blue skies. And most will likely surprise us, because nature's creativity far exceeds our own. In the vast sample of planets we've uncovered so far, we have yet to find an exact twin of Earth, but we have only just begun to explore. The search goes on, becoming more refined each year, and as it does, the dream that once belonged only to storytellers, the dream of other inhabited worlds, grows ever more plausible. With so many planets out there, the question is no longer, do other Earths exist, but rather, how many are out there, and what are they like? Our journey among these myriad worlds stirs a profound realization. If the universe offers so many possible homes for life, could it be that life has taken hold on at least a few of them? It feels almost inevitable to ask this next question. As our thoughts turn toward the possibility of neighbours in the cosmic ocean, we find ourselves at one of humanity's oldest and deepest inquiries. With the knowledge of uncountable planets surrounding us, we now face that question with fresh wonder. In all this immensity, are we alone? Through our journey across the cosmos, from galaxies and great webs of matter to a multitude of distant worlds, a single question has been growing ever louder in our minds. Are we alone in this vast universe? Since ancient times, under the canopy of stars, humans have wondered if there are other beings out there gazing back across the cosmic gulf. Now that we know there are countless planets beyond our own, the question gains even more weight. With uncountable worlds scattered through space, could Earth really be the only cradle of life and intelligence? Or is the universe teeming with life, with other minds looking up at their skies and asking the same question? Life on Earth is our only example so far, but it is a compelling proof of concept. Here on our planet, life arose relatively early in Earth's history, and over billions of years, it has adapted to every niche and extreme. Microbes flourish in boiling hot springs, in the crushing darkness at the bottom of the ocean, and even inside rocks deep underground. Life finds a way in places that, at first glance, seem utterly inhospitable. This resilience and tenacity suggest that if the conditions are even marginally right, life might spark and take hold. Earth has shown us that life needs only a foothold, some water, some warmth, some chemistry, and it can bloom into a myriad of forms. When we look at the newly discovered exoplanets, many are certainly too hostile for life as we know it. Raging gas giants, or sterile rocky worlds baked by radiation. But amid the catalogue of worlds, there are some that appear to have gentler environments. We've identified planets in the habitable zones of their stars, where temperatures could allow liquid water to pool on the surface. On some, if they have atmospheres, rain could fall, and rivers might run, carving landscapes, perhaps not unlike our own. It's on these temperate, water-friendly worlds that we focus our hope of finding something alive, even if the odds of life starting on any given planet are low. The sheer number of planets means there could still be many living worlds out there. Our own solar system offers tantalizing hints that Earth might not be the only place with life. Mars, now a cold desert, once had liquid water flowing across its surface eons ago. We have seen dry riverbeds and minerals that formed in water, and even today, water ice lies frozen at its poles and in the soil. Scientists wonder if tiny microbes might have lived in Mars's wetter past, or even persist in some damp underground niche today. Meanwhile, Jupiter's moon Europa and Saturn's moon Enceladus both hide global oceans beneath thick crusts of ice. These dark, sunless seas are warmed by the gentle tug and pull of gravity, and on Enceladus, geysers of water spray into space, hinting at warm hydrothermal vents on an ocean floor below. On Earth, life thrives around undersea vents without sunlight. So could it not also thrive in the lightless ocean of an ice-shrouded moon? Titan, another of Saturn's moons, has lakes and rivers of liquid methane on its surface and a thick golden atmosphere. It's a frigid, alien environment, but complex organic molecules form there, raising the question of whether some form of chemistry could live in liquid methane, just as ours lives in water. Thus, even within our own star system, there are multiple places we yearn to explore for signs of life. We have sent robotic emissaries to Mars to sift the soil for organic molecules and subtle clues of past or present biology. We have flown probes through the plumes of Enceladus to taste that moon's subterranean ocean. In coming years, new missions are planned to land on Europa or return samples from Mars, all with the hope of answering that haunting question: has life arisen elsewhere in our little corner of the cosmos? So far, these explorations have not revealed anything conclusive. Mars has tantalized us with occasional bursts of methane in its atmosphere, methane which, on Earth, can be produced by microbes, though it can also come from geologic activity. On Mars, that methane source remains unclear, a puzzle teasing us from millions of miles away. The data from Europa and Enceladus hint at the ingredients for life: water, energy, organic molecules. But we haven't yet pierced their ice to see what actually swims, or doesn't, in those dark oceans. In short, the book on life in our solar system is still open, its pages waiting to be written by future explorers. What about intelligent life? Life that builds tools, imagines, and perhaps reaches out beyond its own world. For over half a century, we have been actively listening for signals from other technological civilizations among the stars. Using giant radio telescopes, projects collectively known as SETI, Search for Extraterrestrial Intelligence, have scanned the sky for any hint of artificial radio transmissions, anything that stands out from the natural background noise. The idea is that a sufficiently advanced society might use radio waves to communicate or inadvertently broadcast signals that we could detect over interstellar distances. In 1977, one such listening experiment recorded a sudden, strong signal that appeared to come from the direction of the constellation Sagittarius. It was a narrow-band radio signal that didn't look like any known natural source. An astonished scientist scribbled "Wow" next to the data printout, and to this day, it's remembered as the WOW signal. It lasted just a minute and was never heard again. Was it a faint hello from a distant civilization, or simply an earthly signal that bounced in an odd way, or a quirk of the instrument? We may never know, but that lone, perhaps, fuels our imagination. Apart from that event, however, no confirmed artificial signals have been detected in decades of searching. The skies, it seems, are largely quiet. This great silence is sometimes called the Fermi paradox, after physicist Enrico Fermi, who famously asked over lunch one day, "Where is everybody? If the universe is full of other technological civilizations, why haven't we seen evidence of them?" Many possible answers have been proposed. Perhaps intelligent life is exceedingly rare, or typically short-lived. Maybe civilizations self-destruct, or lose interest in the wider cosmos. Some have suggested that advanced beings could be observing us silently, abiding by a kind of cosmic no-interference rule, the whimsical zoo hypothesis. Or it could be that the gulf of space and time is simply too vast. Civilizations might be so distant in space or separated by so many millions of years that intersecting with one another is extremely unlikely. It's also possible that we haven't been listening in the right way or with sensitive enough ears. Our own radio broadcasts, from early television, radar, and radio, have been leaking into space for about a century, and they've formed an expanding bubble roughly 100 light-years in radius. 100 light-years is a tiny fraction of the Milky Way. Beyond that bubble, Earth's presence is undetectable by those means. If other societies are similar, perhaps their signals simply haven't reached us yet, or ours haven't reached them. The universe is immense in both space and time. It could be teeming with life and intelligence, but spread out so thinly in the ocean of space-time that few ever meet. Despite the silence, our efforts have not been in vain. In reaching out and listening, we've begun to define our place in the cosmos more clearly. We've also developed new ways to search. One promising path is looking for biosignatures on exoplanets, that is, signs of life's activity in the atmospheres of distant worlds. Powerful new telescopes can analyze starlight that filters through a planet's atmosphere when the planet transits in front of its star. If that atmosphere contains an unusual mix of gases, say, a lot of oxygen alongside methane, it might indicate active biology on the surface below. Since oxygen, for example, is so reactive that without life constantly replenishing it, it would disappear from Earth's air. In the coming decades, we may get our first hints of life on a planet circling a far-off sun by this method. We ourselves have not been shy about sending messages either. Apart from our radio and television leakage, we've deliberately beamed focused signals toward a few nearby stars, essentially saying, "Hello, we're here." We've also launched artifacts that carry our story beyond the solar system. The Voyager 1 and 2 probes, which have now traveled into interstellar space, each carry a golden phonograph record etched with images and sounds of Earth, music, greetings in many languages, the laughter of a child, the sound of surf and birds and whale song. It's a cosmic message in a bottle, cast into the vast ocean of the galaxy. The Pioneer 10 and 11 probes bear plaques inscribed with a map of our location and figures of a human man and woman, sent with similar hopeful intentions. The chance of these ever being found is infinitesimal, but the act of sending them is a reflection of our optimism and curiosity. It says something poetic, that even if we are lonely, we reached out in friendship to the unknown. Whether or not we are alone, the very act of searching has profound implications. If someday we detect even simple organisms on another world, say bacteria on Mars or in Europa's ocean, it would prove that life is not unique to Earth, that the spark of biology can ignite elsewhere given the right conditions. If we were to find unmistakable evidence of an alien civilization, a signal, a probe, anything, it would likely be one of the most transformative moments in human history, altering forever our view of ourselves and our place in the cosmos. On the other hand, if time passes and evidence suggests that life, especially complex, intelligent life, is extraordinarily rare, then we come to realize how precious our own living world is. In that case, we might be the universe's sole witnesses. And what a responsibility and privilege that would be, to be the consciousness of the cosmos. There's a chance that life is common, but intelligent life is rare. Perhaps many worlds teem with microbes or forests of simple creatures, but very few ever produce beings who build tools and contemplate the stars. If that's true, then the night sky could be full of living ecosystems, planets with alien biospheres, yet none of them sending beacons or starships. We would still not be truly alone in the sense of life, but we might be functionally alone as intelligent beings until we ourselves venture out. As we ponder these possibilities, something beautiful emerges, a perspective of unity. Alone or not, we share a common origin with everything in the universe. The stars, the distant planets, any hypothetical aliens, we all spring from the same cosmic beginnings. And among ourselves here on Earth, the realization of our rarity, or our potential cosmic kinship with other life, can inspire a greater sense of fellowship. All of humanity lives on one fragile sphere. We are one in the face of the cosmic vastness. National, religious, and ethnic divisions pale when we understand that, to any observer watching from afar, we are a single people bound to a single world. In the quiet, starry night that covers our planet, we continue to listen and hope. The universe has not yet revealed another voice, but we have only just begun to ask. And even if we should find that we are the only ones right now, we can find meaning in that too. It would make us, in a way, the keepers of life's flame, responsible for preserving and spreading the miracle of consciousness. Under the vast silence of the stars, as we await an answer, we take comfort in the journey itself. In seeking others, we have come to know ourselves better. We have learned to cherish our tiny world and to value the life it harbors. The night sky, once merely a backdrop for myth and navigation, has become a profound source of perspective and humility. It reminds us that we are part of a great story, a story still unfolding, full of questions and wonder. In the final quiet moments of our voyage, we reflect on the story of the cosmos and our place within it, filled with gratitude, wonder, and a touch of hope. Our journey through the cosmos has taken us from the grandest structures to the most intimate questions. We have roamed the filaments of the cosmic web and stretched our minds beyond the confines of space and time. We have marveled at innumerable distant worlds and pondered the existence of life and companionship among the stars. Now, as our voyage comes to an end, we pause to reflect on what these wonders mean for us, the tiny observers on a small blue planet. In the end, every exploration of the universe is also an exploration of ourselves. We stare out at the immense night and inevitably turn inward, feeling our own place in it all. The cosmic perspective can be both humbling and uplifting. It humbles us by revealing how vast the stage of existence is and how small our role might seem. Our Earth is a mere speck in a galaxy of billions of stars, which itself is a speck among trillions of others in the cosmic web. But at the same time, this perspective is profoundly uplifting. Against all odds, on this little speck, the universe has become aware of itself. We, made of the universe's own elements, are able to appreciate its beauty and seek to understand its mysteries. Every atom in our bodies was forged in the heart of a star. The calcium in our bones, the iron in our blood, the carbon in our cells, those elements were created in stellar furnaces and released in supernova explosions to drift through space and become part of new star systems. Eventually, they coalesced into our sun, our Earth, and ultimately into us. We are literally stardust brought to life, risen to consciousness. When we gaze at the stars, we are looking at where we came from. In a very real sense, the universe is gazing back at itself through our eyes, marveling at its own grandeur. We are a way for the cosmos to know itself, a brief, bright spark of awareness in the great dark, a tiny piece of the universe experiencing wonder. This realization carries a gentle but profound truth. We are both insignificant and immensely meaningful. Yes, we are small in the grand scheme, one species on one planet, circling one star out of countless stars. But we are also rare and precious, because we bring meaning to the cosmos simply by being here to witness it. The vast emptiness of space becomes a thing of beauty and awe because we perceive it so. In our hearts and minds, the universe has a voice and a listener. The perspective gained from our cosmic journey can fill us with gratitude. All the beauty and life we cherish exists on a fragile world that hangs in the blackness of space like a lonely jewel. From out there, as many astronauts have noted, there are no borders visible on Earth, just a single, gleaming home where all of human history has played out. The vastness above can make our everyday troubles seem a bit smaller, and it reminds us of the common bond we share with all people and living things on this pale blue dot. We are fellow travellers, siblings under the same atmosphere, united by the shared fate of our tiny world. In the cosmic perspective, our petty differences fall away, and what remains is a profound sense of unity and responsibility. This is our home, our only home for now, and it is up to us to care for it and for one another. Knowing what we know now about the cosmos, the night sky will never look quite the same. When we see Orion, or the misty band of the Milky Way, we can think about the spiraling arms of our galaxy, the stellar nurseries where new suns and planets are born, and the ancient stars going supernova to seed the galaxy with heavy elements. We might recall that beyond the Milky Way lie innumerable other galaxies, each with its own stars and planets, and perhaps its own seekers of truth. The sky becomes not just a backdrop of points of light, but a dynamic, richly textured map of space and time. And yet, despite the unimaginable distances and scales, we feel a kinship with it all. The hydrogen in our bodies was created in the Big Bang. The oxygen we breathe was cooked in a star's core. We are children of the cosmos, connected by blood, quite literally made of stardust, to the universe's very beginning. With this awareness comes a calm sense of belonging. We may be small, but we are not insignificant. We are part of something vast and beautiful. The universe is mostly space and silence, but it has also given rise to beings who can love and dream and wonder, and that gives the void a voice. In that sense, we are not lost in the void, we illuminate it. The cold darkness of space is paired with the warm radiance of our consciousness. We carry the universe within us in our atoms, and we carry it in our minds and hearts as we contemplate it. As we think about the future, the cosmos inspires us to dream beyond our horizon. Perhaps one day, distant descendants of humanity will sail out among the stars we have so long admired from afar. They may build new homes on other worlds, turning those points of light into familiar suns in their skies. In doing so, life that began on Earth would spread, making the universe a little less lonely. And if it turns out we are the only intelligent life right now, then these future journeys would carry even more significance, as if we bear the responsibility to bring meaning and life to the lifeless corners of the cosmos. For now, we have the gift of the present moment beneath the stars. We can step outside on a clear night, feel the cool air of evening, and look up. The light that reaches our eyes left those stars long ago, in some cases before we were born, in others before civilization began, and in many cases before humans even walked the earth. We are catching photons that have been traveling for hundreds, thousands, even millions of years across space, only to end their long journey by gently illuminating our gaze. In that moment, the ancient starlight connects us to distant places and times. We are, for an instant, in communion with the cosmos. We can take a deep breath and feel that connection, feeling both the quiet of the night and the subtle, ever-present connection to a larger whole. This journey has shown us violence and tranquility, extreme enormities and delicate connections. It has shown us that even in what appears to be empty darkness, there is structure and light, sometimes visible, sometimes hidden, but always present. It has shown us that as we reach outward for knowledge, we also reach inward toward meaning. And it has shown us that even as we face the immense unknown, we carry within ourselves the tools to find our way: curiosity to ask questions, science and imagination to seek answers, and a sense of wonder to appreciate it all. These are our guides, our compasses, as we navigate both the outer universe and our inner universe. As we conclude our voyage through space and time, let us carry the wonder we've felt back into our daily lives. The universe will continue to unfold its story for eons after we are gone. New stars will ignite, old ones will fade away, galaxies will collide and merge, the cosmic web will stretch and evolve. Perhaps other life will arise on distant worlds, or perhaps far future intelligences will puzzle over the same questions we have. We cannot know how the grand saga of the cosmos will progress, but we have been fortunate to witness a few chapters of it. In the quiet stillness of a starry night, when you feel the weight of the world easing, remember that you are part of this magnificent cosmos. Your atoms were born in stars. Your awareness is a brief, shining beacon in space-time. Let that thought be a comfort. In the face of eternity, here we are, together, alive in this moment, able to ponder the very stars above. Now, as you drift into gentle dreams, imagine the stars overhead, shining their ancient light down like silent guardians. Envision the Milky Way arching across the sky, a river of countless suns embracing the darkness. Feel the peace of knowing that you belong to this universe, and it belongs to you. Though the cosmos is vast and deep, It cradles us in its mystery and beauty. We end our journey with hearts full of wonder and minds at peace. The cosmos is vast, but it is not cold to us, for we have found warmth in its splendor and our connection to it. Under the eternal night, we find not loneliness, but profound companionship. The starlight, the quiet, and the knowledge that the story of the cosmos is our story too. Good night, and sweet dreams among the stars.